Okay, good morning, everybody. My name is Andrea Malchiodi, and I'm the current director of the De Giorgi Mathematical Center. So I would like to welcome you first to the meeting, Parameter Spaces in Complex Dynamics and Related Topics. I will just say a few words about the De Giorgi Center and promise I won't take much of your time. The center was founded about 20 years ago, formally as a research laboratory of Scuola Normale Superiore, but with a goal of being an aggregation center for the mathematical community of in Pisa, which of course includes many people from the University of Pisa and also a small community from the Scuola Superiore Sant'Anna. So these institutions, especially the former, contribute substantially to the activities of the center. So since the foundation, the main activities of the center have been workshops, intensive research periods, and also we started recently a colloquium series. We have visiting positions of two types to perform research in pairs for short periods, and also we have 2 years postdoctoral positions with open like every year. I'm basically done, so I would like to thank the organizers and the committee for the organization of this really nice event, and also the staff of the center for their constant and valuable support. Thank you.
So let me start with the most important thing, which is to thank you all for coming here and to thank the Centro De Giorgi for helping organizing this conference, and also thanking the Centro De Giorgi, the University of Pisa, and Carlo Carminati, and Stefano Marmi with some UniCredit funds from the Scuola Normale for making this possible and funding the conference. And let me also give you some practical information. So the most important one is if you are giving your talk in PDF, please send the slides here to the address which is written here. And also if your EduRoam happens not to be working, then here there is a Wi-Fi network that you can use. We have a fantastic technical support. Today is Francesco, but it will turn over the week. And another important information is coffee breaks. Okay, so coffee breaks are not here. They are in the garden of the Scuola Normale. So we will all walk towards the garden, and there is a bonus to the coffee breaks, which is a poster session. Every day we will have a few different posters, and they will hang for the whole day, and you can ask questions to the authors of the poster. Last but not least, lunch is on your own. And basically, any kind of restaurant that you will get in Pisa will be fine as long as it is below Piazza dei Cavalieri. So just don't go towards the tower. Anything else will work, okay? And have fun, enjoy, and let's start.
Okay. Anyway, I'm going to do my job as a chairwoman for this morning, and I'm just going to welcome. It's really, really a pleasure to see Laura here. So Laura De Marco will give the opening talk of this conference, and she comes from Harvard, as you all know, and we will hear about bounded geometry for PCF points in MD. Thank you, Laura.
Thank you. Thanks for the invitation. It's good to see all of you here. Yes, I do at some point before the end of the talk want to talk about bounded geometry of PCF points, which is a new result that I want to present. But I thought since I'm the first speaker of this event, I should go slowly and try to introduce you to the spaces themselves, the moduli spaces of maps on the Riemann sphere. It's a parameter spaces conference. The moduli space is not really a parameter space, strictly speaking, but close enough. So I want to say a few words about geometry and arithmetic of what I'll call MD. So MD will denote, as I said, what I call the moduli space of all maps on the Riemann sphere, so which I'll denote P1, over the field of complex numbers of a given degree, of degree D, where, as usual, we assume that the degree is at least 2. So of course, what is this? This is where the space of all maps. One might denote let's say rat sub D just as a set, the collection of all rational functions, ratios of polynomials that have degree d with complex coefficients. And then the moduli space is just the quotient of this space by the usual action, conjugation by Möbius transformations. So MD here is just this space of all rational functions modulo the action by conjugation of the group of Möbius transformations. Now, as a space, what is it? Well, let's see. We know, for example, that the dimension of this space is 2D minus 2. Of course, the dimension of this space is, of course, the number of coefficients, but they're only expressed up to scale. So the dimension of this space is 2D plus 1. The Möbius group there is three-dimensional, so we're left with dimension 2D minus 2. And it's worth observing that this dimension is the same as the number of critical points of a given element of this space. So this is the same as the number of critical points counted with multiplicity. Of any element in the space. Let's try again here. Are there some larger pieces of, here. Yes, thank you. Great. Let me take a couple. Okay. All right, so what do we know about this space? Before I say anything about dynamics, it's helpful to know what is this total space of all maps. This one here, you can think of, if you parameterize by the coefficients, it's just a certain open subset of a complex projective space where you just throw out the ones where you have common factors between P and Q. So you have some nice big open subset here. This is just the quotient space. As such, it inherits some algebraic structure. And so MD has the structure of an algebraic variety, in fact, an affine algebraic variety. Working over the field of complex numbers, you can think of it then as a complex affine algebraic variety. But it turns out it has a little more structure. In fact, one can think of it as an affine algebraic variety defined over Q. So just to emphasize, this MD actually properly embeds into some affine space, or of course also into some projective space. And we can define it via some map defined. You can think of it as an algebraic variety defined by polynomials with coefficients in the field of rational numbers. So affine. Now, some of you might recall that in an article by Milner 30 or so years ago, he observed that in degree 2, it has a very simple structure. That M2 is just isomorphic to the affine space itself over the field of complex numbers. One can think of it as just a copy of C2, and he gave us natural coordinates on this space. If you just take any element, any degree 2 rational function, it has 3 fixed points. And so you can parameterize this space by that collection of multipliers at the fixed points. Those 3 numbers, they satisfy a relation, and it gives you that this space is isomorphic to C2. So in that particular case, M2 is an affine space. And in general, I should say MD is sort of almost an affine space in the sense that we know that it's not just some affine algebraic variety, it's in fact a rational variety. This was proved by Levy some years ago. MD is rational. In other words, it's, as we say, birationally isomorphic to an affine space. There's some big open Zariski open set in here, which is isomorphic to some Zariski open of the affine space. But that's maybe not so helpful because unlike in degree 2, it's not a manifold. it's not smooth. So for all degrees bigger than 2, it has singularities. So I'll just mention, so MD is not smooth for all D bigger than 2. This is not too hard to see. So in Milner's paper from around 1990, he had observed that this MD, while not a complex manifold, has the structure of a complex orbifold. Locally, you can think of points as quotients of something nice modulo a finite group because of the finite automorphisms. So that this quotient here, has some of the maps are preserved by that conjugation action because they have automorphisms, and that's what leads to this singular structure. So the singular locus is precisely the locus of maps with automorphisms. So this comes from automorphisms. So this is certainly expected. I hadn't seen it in the literature, but I realize now it did appear. It's explicitly stated what the singular locus is in an article of Myasnikov, Stout, and Williams. Oops, broke another piece. Yikes. All right. So if you're looking for a reference for this, you'll find it there. There are a couple other things I wanted to tell you about these moduli spaces. So I said they're like affine spaces. Also, not only are they not smooth, they're not all simply connected. Of course, M2 is simply connected. I said it's just the affine space, but actually the even degree ones are in fact all simply connected, but the odd degree ones are not. So just in case you're interested to know this, pi1 of MD happens to be, well, 0 if D is even, but Z mod 2Z if D is odd. This was proved recently in a project of one of my former students, Khashayar Philom, in collaboration with 2 topologists, so people who did not really come to the subject from dynamics. So Bergeron and Philom and Nariman. They worked out. They also showed, by the way, it's not only that it's, well, it may be simply connected, but it's not contractible for degrees, forgot what their bound is. I think for all degrees, at least 7, it's not contractible. So even though it's simply connected, I said it's like an affine space, but it's really not. I mean, it's got some structure there. So it's not contractible as a space for all degrees, I think greater than or equal to 7. I don't remember the state of the art. I don't remember if they said that maybe in degrees 4 and 6 it is contractible. I don't remember, but it's probably in their paper. Okay, I'll put this up. Oh, can you see that? I guess so. All right, so there's just some general properties of this moduli space. Of course, we do dynamics, and so maybe we're not so interested in the structure of the space itself. What we'd really like to know, let me just draw a schematic picture. Oh, I had meant to start a timer when I began speaking, and then I forgot to do that. So I don't know what time I started. Okay. So of course, what we'd really like to know is within our big moduli space of dimension 2D minus 2 is, what is the structure of the bifurcation locus, and what do the stable components look like, and what kind of dynamics do you have? So this funny picture is supposed to represent sort of the bifurcations. Say in the theory of J stability. That is to say, so here this would be the stable part. We have this open and dense pieces of these space of conjugacy classes corresponding to stable maps in the sense of Monnier, Sod, and Sullivan, and Lyubich from the early 1980s, who developed for us the theory of stability. And the bifurcation locus is this complicated fractal subset of the moduli space. So of course, you should imagine that you have all these Mandelbrot sets and the like inside the bifurcation locus. It's a very complicated and interesting set. And we don't have, I mean, we have a far from a complete understanding of the structure of these stable components and what is all of their topologies, but there are a lot of developments over the years studying the structure of these things that I won't talk about because what I wanted to address, what I just erased, was the geometry and the arithmetic of this moduli space. So as an algebraic variety, even an algebraic variety over Q, there's more structure there. And that the hope is that maybe that extra structure can inform the dynamics, that it tells us something about the dynamics. And so let me give you a little bit of information of what I mean by that. So what sort of arithmetic am I thinking about? Okay, so closely related to this picture is an arithmetic object, which we call the critical height. It was introduced by Joe Silverman roughly 20 years ago or so. Which I will denote by h hat sub crit. So this is a function defined on not on all of the complex points of our moduli space, but the points that are algebraic. So on the algebraic points of the space, it's a real valued function, in fact, a non-negative real valued function. And what does it measure? So heights, very generally, measure arithmetic complexity. You have, MD, you're thinking of as sitting inside, in this case, some affine space. So the Q bar points correspond to the points all of whose coordinates are in this the algebraic closure of Q. And we can talk about the complexity, the arithmetic complexity of those numbers, of the coordinates themselves. So heights, as introduced by Weil on a variety, is some way to measure arithmetic complexity. And Silverman's critical height was introduced to measure arithmetic complexity of the dynamical system. It was something very specific to this moduli space. And so just to say a few words about how it's defined, this is measuring, maybe I'll say it in words over here. So this measures some arithmetic complexity of what? So it's of, say, the conjugacy class of F. So I'll use this. So F is, say, a map, and this will represent the conjugacy class. So what would this mean? To say that the conjugacy class has all of its coordinates in Q bar just means that there's some representatives, there's some actual map whose coefficients can be expressed over the field of algebraic numbers. Okay, so there's some presentation that doesn't involve pi's and e's. It's all written with algebraic numbers. So this measures the arithmetic complexity, but via what? Via critical orbit behavior. I'll write down a definition in a second. And what I want to emphasize after I write it down is that this definition gives us actually some information about this picture, this schematic picture in terms of the bifurcations in the family. So the definition that he provided was the following. So the critical height of a conjugacy class is what? We choose any representative, which is in fact defined over Q bar. So we choose some F in this conjugacy class whose coefficients are in Q bar. And then we look at all of the critical points of F prime of C equals 0, counted with multiplicity, and evaluate what? We look, for each critical point, we look at the growth rate along the orbit of the critical point of a height. Okay, so here I'm not giving a definition, but H here represents any choice, the standard choice of some V height, which is a way that we measure, as I said, arithmetic complexity of numbers, actually. So So the idea, please don't worry too much about the definition if you haven't seen heights before. What I just want to emphasize that there's a good way to measure complexity of numbers, of actual numbers. Forget about infinity, but just of actual numbers. And then this is saying, okay, we know that along an orbit, if f has degree d, one expects that that complexity grows like d to the n. And so one could look at this growth rate along the orbit and then evaluate, take its sum over all the critical points, and this gives us a number. And this number is what he calls the critical height of this conjugacy class F. Turns out it's invariant. It's a conjugacy invariant. It doesn't, these values will be the same, independent of the representative you choose. So it's supposed to measure complexity. Okay, but what is it? So as I said, it's some real valued function. It's non-negative. It has some very complicated features, but there are two features that I want to emphasize about this function. The first is, okay, it's non-negative. The minimal complexity points are things that we understand in dynamics. So the minimal complexity points, in other words, the zeros of this critical height, are precisely the post-critically finite maps. So over Q bar. So if your conjugacy class is defined over Q bar, then we can even talk about this height. So remember, I'm only looking at classes over Q bar. So this does not include certain flexible lattice maps because it's not even defined at some of those maps. But for most of them, it is. And if one can unwind the definitions and use some properties of heights, and it turns out that minimal arithmetic complexity in this sense coincides with minimal dynamical complexity in another sense. So what is PCF? PCF is just my shorthand notation for post-critically finite. In other words, the maps for which each of the critical points has a finite orbit is pre-periodic. And one can see that if the orbit is finite, these numbers are all zero, but the converse turns out to also be true, just from properties of heights. Okay. Right, so the minimal complexity are precisely the post-critically finite maps, which we learned from the work of Thurston, from the work of Duhady and Hubbard, from sort of the early days of complex dynamics, that these are important, that they play an important dynamical role. And this tells us they also play, they have an interesting arithmetic role to play. And there's one more thing I want to tell you about this height to motivate the rest of the story of the talk, which is that this height knows this picture. The height knows this picture in the following sense. So the function can detect bifurcations. And how does it do that? Of course, it's only defined on the algebraic points. But this height, as with all height functions, they satisfy certain nice properties. This height, I should emphasize, I said the moduli space is defined over Q. So it turns out this height is invariant under a Galois action. So it turns out that it can be decomposed into a very natural infinite sum, which has the following form, which I'm going to write as, say, h infinity plus an infinite sum over all the primes p of some other function, say h sub p. Okay, so it has actually a very natural, not canonical, but anyways, can be decomposed into an infinite sum of some function which we associate to each prime and something which we associate to a function on the underlying complex points. And whatever this is, this can be extended, has some nice properties, and it extends continuously to the complex locus. In other words, all of the maps that we usually talk about as people in complex dynamics. So this, what we call Archimedean piece of the height, defines actually a nice function on the underlying complex algebraic variety. And what is that function? Well, it turns out it's a potential for the bifurcation current whose support is on is equal to this bifurcation locus. So potential in the DDC sense, so this as a function on this not quite complex manifold, but complex orbifold, DDC of it is precisely what can be called T-BIF, or what I call the bifurcation current, which is something I studied in my thesis. And sort of the only thing you need to know about this really is, well, what is this? This is a generalized form whose support is equal. Where do I write? I'll write it here. Support. There's not a lot of light on the board itself, but can you all see what I'm writing? I hope it's okay. The support of T-BIF is precisely equal, both on the total space and in any slice, in any parameter space, is equal to the bifurcation locus itself. So it knows the bifurcations. So as a set, the support is equal to that. Okay, some 1-1 form type object in the distributional sense, whose support is equal to the bifurcation locus. Okay, so this height knows about bifurcations. So quite interestingly, there's this interplay between the arithmetic of the underlying algebraic variety, defined in this way, and the dynamics itself. Are there any questions before I go on? Just general questions. Oh. And so that background was all to motivate one of the questions that I've been thinking about a lot over the last, well, more than 10 years now, which is, I'll write it vaguely, sort of how does this arithmetic inform us about the dynamics. And let me give a more concrete example, a more concrete question that some of you have not only heard about, but in fact worked on and proved cases of. So one sort of more explicit question was, I've been trying to understand for many years, how shall I say it? The structure not only of MD itself, but of the subvarieties in MD, which are arithmetically minimal complexity, which are arithmetically small, shall we say? Height is we can say small to say small height. Which subvarieties, or in other words, which families, which one parameter families are actually minimal complexity in this sense? And so one way to formulate that precisely would be the following question. Actually, let me give a definition first and then make a more precise question. So I will say a family of maps, or an algebraic family. So let's say an algebraic subvariety, say X, inside MD, which again, remember what we're talking about, spaces of rational maps on P1. So this is just some family of maps on P1. I'll say that an algebraic variety, here, let me give you a definition, is special, arithmetically special, critical height special, if it has lots of minimal complexity points. So if there are lots of zeros. So if the PCF points, so the zeros of the height, are sort of span the whole space. In other words, are Zariski dense in X. Okay, remember what this means to say that a set, and it's not a room of algebraic geometers, a set is Zariski dense if it's not contained in a proper algebraic subvariety. So the smallest algebraic subvariety containing those points is all of X. Okay. So I'll say that X is special if its critical height is small, which really means there are lots of zeros from the algebraic or arithmetic point of view. And so I've been trying to understand for a long time, well, how do we understand these? Which are the special families? which are the special families? So one could reformulate this question. A specific instance of this vague question is sort of which families are in fact special. Okay. Does that show up? Yes. Okay. Eraser. Okay. So let me give you just a couple examples to have in mind. And hopefully I'll be able to state a theorem before I run out of time. Okay, so an example of a special maybe the first observation I should make is that the entire moduli space is special. There are lots of post-critically finite maps. They're scattered all about in our moduli space. They're not contained in any proper subvariety. That requires some proof. It's not completely obvious, but with the complex dynamics results that we know, turns out it's not too hard to prove. Okay? So MD is in fact special. And other examples that are special, the sublocus of polynomial maps. So if you look at, say, the conjugacy classes of polynomials, this is also special. They're in any, for example, well, in any family of all polynomials. So you take, say, the quadratic polynomials with its Mandelbrot set. What are the PCF points? They're the centers of the hyperbolic components and all of the Misiurewicz points in the boundary of the Mandelbrot set. There are infinitely many of them, so there's Zariski dense. The smallest algebraic subvariety is the entire one-dimensional family. So those are examples. Another example I want to emphasize, because I'll come back to it, is say inside, let me just focus on degree 2 for a second. So in the degree 2 space, so the polynomial slice, well, I've already mentioned, so that's a line in the, remember in the degree 2 case, M2 is isomorphic to just the affine space C2. But there are all sorts of algebraic curves that are special in M2. So for example, if you take the curves pure N0, so this is the notation that Milner used to define the collection of all conjugacy classes of degree 2 rational functions for which f has a critical point of exact period n. So one critical point is periodic with exact period n. And you may recall this is a one-parameter family of maps. And he uses this notation pure N0, periodic of period n, exact period n with multiplier 0. That's where the 0 comes in this notation. These are special curves. These are special curves. And in complex dynamics, maybe you know why. If you have a one-parameter family, if one of the critical points is persistently periodic or pre-periodic, there's a free critical point, which is creating the bifurcations in the family. And that other critical point has finite orbit infinitely often because there are bifurcations along this family. So there are infinitely many post-critically finite maps in this family, so it is special. Okay? And in fact, all of the examples, well, maybe I'll mention one more from degree 2. I mean, there are others. Another kind of example that would be special would be, say, the automorphism locus in degree 2. That is to say, so the maps that have automorphisms, so let's say you parameterize them by what? What's the usual way to parameterize them? What do people write? Z plus 1 over Z times a constant, maybe? Where Z goes to minus Z is the automorphism. In any case, what I want to emphasize is in the automorphism locus, which is itself a one-parameter family, the two critical points have a symmetry. One of them has a finite orbit if and only if the other one has a finite orbit because there's an automorphism that interchanges the two critical points. So So the two critical points, they behave the same. So anytime, because there are bifurcations, at least one of them has to have finite orbit infinitely often, therefore the other does, therefore those are all post-critically finite. And so that's another example of a special curve, a one-parameter family inside M2. And in looking at these examples and trying to understand, again, I think of all of these as arithmetically minimal, arithmetically simple, they share a feature. I mean, they all, by their very nature, come from conditions on the critical points. Here, where a critical point is periodic, here, where the two critical points are related, here, where one critical point is fixed with maximal multiplicity. So each of these examples, and here where there's no condition at all, because it's the total space. So each of the examples comes from some condition on critical points. And so some years ago, in some work with Matt Baker, we had just formulated, maybe somewhat vaguely, but we formulated a conjecture where we believe that all of the specials should have this form. The only way that a family can have lots of post-critically finite maps, the only way that a family can be special is if it is defined by critical orbit relations. If it is defined by critical orbit relations. So X special, if and only if it is defined. This is, again, a vague way to formulate it, but I don't want to get into the details of what I mean by a critical orbit relation. It is defined by critical orbit relations. Okay, where, in other words, where, say, one critical point lands on another persistently in the family, or one critical point is prefixed throughout the whole family, or there's an automorphism that interchanges two critical points. These types of things would qualify as critical orbit relations. We don't actually have a classification for general maps on P1 of what those relations actually could be, which is why I really can only formulate it in some vague way. But in the case of polynomials, we do have explicit classification. And I want to emphasize this, I want to mention two theorems. So this is still open. Sorry, let me just emphasize this conjecture is not resolved, and I cannot resolve this conjecture in full. But it is known in the case of curves, one-parameter families. We do now know all of the one-parameter families, which are special in this sense. And its most general form, most recently, there's an article of G and Xie, which resolves it for one-parameter family. So in other words, for algebraic curves in MD. But building on actually lots of examples that we're also treating curves. And I want to point out, not only because Charles in the audience, but because I think it's a really nice result. In some work of Charles with Thomas, they resolved and very explicitly resolved the case of curves. In other words, again, one-parameter family. I got chalk in my pants. Okay, there. For curves in polynomial spaces. So theorem, conjecture holds. The conjecture is true in the setting of, so again, only for one-parameter families is this resolved. So in this case, I said we don't have an explicit classification in general of what the relations can be, but we know what a general notion of relation should be, or is in some abstract sense. So that's what's resolved here. But in the case of polynomials, where we do know relations, say building on the work of Rit from the 1920s, we know what the relations are. We know what the symmetries are. And so in their work, they sort of gave an explicit classification of what the special curves are for families of polynomials. So that is basically where we are with this story. How am I doing on time? 9:42. But for example, two-dimensional, two-parameter families is still wide open. Okay, we still don't know what happens in higher dimensional. And remember, the space, this is dimension 2D minus 2. So as D gets large, it gets big. So we're still pretty far from understanding what these special subvarieties are when it's not a one-parameter family. And even in the one-parameter case, there are still some interesting questions that we haven't fully resolved. So let me now state a theorem to tell you what I've been working on most recently. And as of this morning, I noticed that my Dropbox was updating and my co-authors are doing some final revisions, and I believe that this will be posted today or tomorrow. So anyways, so it's not yet available on the archive, but hopefully it will be before this conference is over. So here are a couple of theorems. So this is joint work with two co-authors, with Mirto Mavraki, who's now in Toronto, and Hesi Yi, who's at Zhejiang University in China. And so let me state two theorems. The first is that, well, okay, both of them are of the following flavor. I cannot resolve this conjecture. We cannot give a complete classification of the specials in higher dimensions, but we can control their geometry. We can control their geometry in some uniform way. So both of these theorems are about controlling the geometry. So the first is that I haven't, well, that's okay. Let me just say something and define things after. So the first is that given any D, which is the degree of the map, and say capital D, which is going to refer to the degree of subvarieties, given any little d for degree of the map and capital D degree of subvarieties, there are only finitely many special subvarieties, say X, in MD, non-trivial families. Positive dimensional, sorry, before I finish my sentence, there are only finitely many positive dimensional special subvarieties of degree less than or equal to D, of geometric degree less than or equal to D. So the geometric complexity of our specials has to grow. I mean, you have some infinite, there are infinitely many specials, I should emphasize. There are lots and lots of special subvarieties defined by critical orbit relations, or perhaps by other things, because we don't know the conjecture. But whatever they are, their geometric complexity has to grow. There are only finitely many of some degree. Now, how many? I have no idea. I don't know. It's not an effective control. I have no idea how many there are as a function of the degree of the map and the degree of the variety. I'd love to know. But right now, all we can say is that this number is finite for each D. So this is the first theorem. And then the second, oh, I've taken up the whole board. I wrote too big. The second theorem is a little bit more technical. Well, I'll just write it up there. And then I'll give some examples of some consequences of theorems of this sort. Let me leave that there. I'll erase some of the special examples because I'll come back to this example here. Oh, it occurs to me before I state the next theorem, so theorem 2, that, so the notion of degree, I mean, I said MD, I mean, it's not just an affine space. So I'm not saying, it's defined by one polynomial of degree less than or equal to D. One should think of it as, so in order to even define, sorry, let me add this here. There's space here. Or in order to even define what I mean by the geometric degree for an abstract algebraic variety, it requires, I need to make a choice. I need to make a choice. So I can think of MD, as I said, as sitting inside some affine or some projective space. So for each degree D, we fix a choice. It actually doesn't matter what choice it is. That would tell you how these numbers grow, but the finiteness doesn't matter. So you fix a choice. And what is the degree of an algebraic variety? So you have some algebraic variety, say you're in Pn, maybe it has dimension R. It's just where if you cut your variety with hyperplanes, sufficiently generically chosen, then and you cut them until you're left with a finite set, and then you count how many points do you have, and that's this notion of degree. So if it's a hypersurface, if it's codimension 1, and you cut with a hyperplane, then sorry, and you cut down, sorry, if hypersurface, it will match the degree of the equation defining it, is what I wanted to emphasize. But in general, it's a little subtle to talk about degrees. It always involves a choice of a variable on your variety, and you have to, talk about this embedding and then make sense of the degree. But for the case of M2, just to emphasize, in Milner's say M2, remember that this really was just a C2. So if you have some algebraic curve inside here, it's given by one equation, and that equation has a degree in its variables. And so that is the degree that I'm talking about. Okay, just the equation, the degree of the equation defining. Okay. All right. Am I running out of time? 9:48. Okay, I'll state theorem 2 and then make some comments. So the second theorem, actually, the first theorem and the second theorem are really all part of one statement, but I think this one was easier to parse. The next one just looks a little more technical, which is, it starts the same. So again, given the degree of the maps and some capital D, which will correspond to a degree bound, the statement is that there exists, so it's uniform control on geometry. So there exists uniform constants, say n, which depend on these, well, uniform in the variety, sorry, depend on this input, and say some other constant that I'm going to call b, again, depending on these input integers. There exists uniform blah, 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 so that any for, get my quantifiers and everything, so that for any complex algebraic subvariety X in MD, which itself has degree less than or equal to D, what do I know? I know that if I look at the post-critically finite maps inside of it, now X, if it's not special, this is not Zariski dense, it doesn't span the whole space, but if I take its Zariski closure, in other words, the smallest algebraic subvariety containing all of the PCF points inside X, the Zariski closure of the PCF points, so of PCF in X, that this subvariety has controlled geometry. So it has less than or equal to n irreducible components. And each of those components has bounded degree. Okay. So for any complex algebraic subvariety, even if it's not special, the specials inside of it have controlled geometry. That's what this says. Uniformly controlled. Independent of the X you chose, only depending on its ambient geometry. Let me give some examples. Let me give 2 examples that I hope will illustrate what these statements mean. The first is an example of the first theorem. I mentioned these pure N0 curves inside M2 that I said were introduced by Milner. Remember what they are. So this is the 1-parameter family of degree 2 maps, which has a critical point of exact period n. Okay? So these are conjectured to be irreducible. We know they're smooth. So in other words, it's equivalent then to saying they're conjectured to be connected. They're conjectured to be connected. So really a 1-parameter family in the usual sense of quadratic maps. Now, we don't know if they're irreducible. Although right at this moment, I want to point out that there will be a talk later this week addressing exactly that conjecture. So let me just refer, before I make my statement, I will say they're conjectured to be irreducible. In other words, connected, because they're actually smooth inside M2. So they're conjectured to be irreducible. And so I want you to see, so Caroline Davis, who will speak on, I don't know which day you're speaking, Thursday? No. Oh, that's tomorrow. Great. So Caroline tomorrow will speak about this question. Actually, Rohini has also recently addressed this question, although I'm not sure if you're speaking about this particular result. So there's work in the direction towards producing irreducibility, but it's still open. We still don't know if it's irreducible, although we definitely believe it. A consequence of theorem 1, oh, I didn't call it a 1. Let's call that theorem 1. Just pretend I put a 1 there. A consequence of the first theorem that I wrote down is that while I cannot prove irreducibility this way, I do know that each of the connected components has degrees growing with n. Okay? That all of the irreducible components have degrees that grow. So the irreducible components, whatever they are, have degrees going to infinity with n. By the way, the degree of this curve itself is what? I don't know. It's approximately 2 to the n, something along those lines. It's the same as it's not exactly 2 to the n. It's the number of centers of the Mandelbrot set, the number of hyperbolic components in the Mandelbrot set corresponding to exact period n, which, as many of you know, is not, there aren't exactly 2 to the n of them, but there's some inclusion-exclusion rule that tells you how many there are, and that's the degree. And so again, we don't know if this is irreducible. Again, irreducible over C as an algebraic curve, a complex algebraic curve. But we do know that the irreducible components have degrees. And you get that from theorem 1, which I claim has something to do with arithmetic. I will probably have no time to tell you how the proofs go. But the second example I want to mention, for corollary, which to illustrate how theorem 2 works, is a family of examples. So theorem 2 implies the following. So these are, I say, uniform bounds. One can think of applying theorem 2 to families of varieties. And one of my favorite families of varieties in degree 2, I talked about this exact example in the conference in Japan honoring Mitsushi Shikura, is the following family. Suppose you're in degree 2 and you consider Milner's pier 1 lambda curves, where lambda varies in the complex plane. Now, these are the curves, the one parameter families of maps consisting of maps with a fixed point of multiplier lambda. So these are all the Fs in M2 for which there exists a point P, which is fixed with multiplier, in other words, derivative lambda. So that defines a curve in M2. In fact, in Milner's coordinates, this is just a straight line. So as you vary lambda, so here's your M2. As you vary lambda, you have this family of lines. They do intersect, but they sweep out the entire M2. Remember, we know that the post-critically finite maps are Zariski dense. So they're scattered about in this space. By the way, pier 1, 0 are the polynomials. Pier 1, 0 are the polynomials. And one of the things you get from theorem 2, sorry, let me erase enough so I can just write down the conclusion before I stop. So one of the things you get from theorem 2 is that actually there exists a uniform, say, what did I call it? N, so that the number of post-critically finite maps in each of these families is no more than n. And this is true actually for all lambda. Of course, for lambda equals 0, the lambda equals 0 case is special. It's the polynomial family. So there are infinitely many post-critically finite maps. That is a polynomial. Pier 1, 0 is the polynomial family. But everywhere else, there's a uniform bound on the number. So even though they're scattered around the space, even though they're scattered around the space in some complicated way in the total moduli space, somehow the way these curves sweep them out, there's some uniform control. I don't know what that n is. So 1 year ago at the Shishikura conference, I conjectured that maybe it's just 1. So Xavier Bouffe immediately told me that can't be. There has to be at least 2 on many examples. So now I'm just going to go ahead and conjecture. But maybe it's actually 2, and maybe 2 is really the answer, that maybe there are at most 2. The example he gave me is great, and I love it, and I just don't have time to tell you what it's all about, because maybe if I can just take 30 seconds to say, yeah, say where, I just want to say one word of, okay, so I wrote some theorems down, but I've told you nothing about where they're coming from or how does one actually prove them, and I don't have time to give the proof. But they're really 2 key ingredients. On one hand, there's the height machinery that I mentioned, okay? And I'm not going to go into that. Please feel free to take that as a black box. The theory of heights and what you can do with them. Okay, but on the other hand, this is really about complex dynamics. So the complex dynamics piece is a study of these bifurcation currents and bifurcation measures on this space. And we use properties of the bifurcation measure in a crucial way. So there's just a couple, sorry, just to give some credit where credit is due. There are a couple references I want to mention, which are really key, have some really key ideas. So I told you that the current itself, what I called T-BIF earlier, was something I had introduced in my thesis, but I didn't really do anything with it. In 2007, so some years later, then in an article of Bassanelli and Bertolo, they introduced a measure, what I'll call, say, mu-BIF, which is the top wedge power of this thing. And they showed this, so this is a measure on the moduli space, and they showed this measure is not trivial, that it's actually non-zero. And they do this by showing that a certain rigid lattice map must lie in the support. Okay, so they show there's at least 1 point in the support, therefore it's a non-zero measure. But shortly after that, I think it was in 2009, in an article of Xavier Bouffe and Adam Epstein, they studied further properties of this measure and showed not just is the one possibly rigid lattice map in there, but actually every rigid PCF map lies in the support. So they showed that rigid PCF maps are contained in the support. And the ideas that they use to prove that, we use crucially. So I need to give them credit. And then the last sort of complex dynamics ingredient, of course, there were generalizations of that. For example, in the thesis of Thomas Gautier and in some other works that were, really inspiring. And then the last reference I want to mention, in 2013, for this complex dynamics side, Romain Dujardin proved a converse type statement that dense in the support, that these things are actually dense in the support. So if you're in this top wedge power of the bifurcation, so you're in the support of this measure, that you can actually find rigid PCF maps there. And we also use that. So it's sort of the converse statement. So these rigid things are actually everywhere dense. And so the tools that he used to prove that related to currents is something we also use. So there's this arithmetic piece and the complex piece, and those are the complex pieces. And I'll stop there. So I just wanted to show.
Thank you so much for this enlightening talk. And are there any questions before we go through?
It's making it maybe effective results.
So we appeal to, we're using specifically the height machinery that we're using is relying on the work of Yuan and Zhang and their arithmetic intersection theory on quasi-projective varieties. And so in that setting, we don't have control over specific constants or anything else. So we just sort of using it directly without trying to go into the proofs and reuse.
More questions?
Hi. So if you consider the parabolic maps like L and lambda with lambda root of unity, and then you relax the condition of PCF, just asking all the critical points except one has a finite orbit. So can you ask the same question in this setting?
Right. So of course, as we know, there are no PCF maps there. It's also the case that so a lot of the uniform bounds and the finiteness statements that we get for PCF do not carry over to the parabolic setting. So here's a very naive reason is that, so with this critical height that I defined, so those are not, so for example, the quadratic polynomials that have a parabolic cycle all have height log 2, which is there's this real gap between log 2 and 0. And so the techniques we have really require that these heights be sufficiently small. And the geometry, I mean, if you're not controlling the period of the cycle, if you have, say, a parabolic, their geometry, they're complicated because they themselves live on real algebraic subvarieties. And there are lots of them on given real algebraic subvarieties. So there's so many more parabolically special, shall we say. I mean, just as in, say, the Mandelbrot set, where, of course, the boundary of the main cardioid and the boundaries of all the hyperbolic components have infinitely many parabolic points. So it doesn't directly answer your question. But I just want to say some of the reasons why I cannot treat parabolic, I mean, which are also dynamically special, but for some reason they don't fit into this story. So I don't quite know how to. You can definitely formulate the question, and yes, so I think it's a good question because I think they're dynamically important, and in principle more important. Oh, and I should say that one of the key things that we use to prove I should have emphasized going into the complex piece. There's one key step where in order to prove something, we take one of these measures on a complicated space, and we have to zoom in, and we specifically choose a parameter where there's a parabolic. And that's crucial for our proof, was to be able to choose a parameter where we have a parabolic, even though we're studying PCF. We perturb so that we get a parabolic, and then we can prove something about our limit when we zoom. So parabolics play a role in the story, but they're not the main characters, and I don't know how to make them the main characters at this point. No.
We resume with the next talk. So it's a pleasure to have Sebastian Van Strien from Imperial College in London, who will be talking about density of hyperbolicity within any non-trivial family of real analytic interval maps.
Well, thank you very much. It's always really exciting to talk in Italy anyway, but in the spring, man, this is the best place to be. Thank you very much for asking me to come here, and in addition to give a talk. So I'm going to talk, my talk is inspired by real one-dimensional dynamics, but of course I use complex tools. So it will really be more, but let me start with some of the intricacies that you may have in real one-dimensional dynamics, which is probably something that most people in complex dynamics don't really study. So, for example, you have the simple behavior where you have a periodic attractor, and I'm just sort of, this is taken from another talk, but you can see here you can have period fixed point or period 3 attractor. This is somewhere, everybody knows that. And of course, you can have statistically very simple behavior. So if you take a typical starting point, that limit behavior, so you record where you've been, and you put the Dirac measure there, and there should be a 1/n here, which is dropped out. Then the Dirac measures will spread out to an absolutely continuous invariant measure. So it means you go and you can actually statistically forecast where you've been. And that, of course, is a case where you have that you have by 4x1 minus x, but lots of other examples, and I won't really discuss that. But let me talk here about the kind of really bad behavior. And that is, for example, that you may have something in F-forward invariant counter set, which is a wild attractor. So if you look at its basin, so the set of points that in forward interest converge to this counter set, that could be have full measure, full Lebesgue measure, and yet topologically meager. So from a topological point of view, it's a very small set, and from a measure theoretic point, a very big set. Vice versa, if you look, there's some interval, and then the basin of that interval will have zero Lebesgue measure, but will be topologically large. So that's there's some. Good. And so that's one kind of weird behavior. So you have these well detractors. And the other kind of strange thing is that you may have something where you have a strange or physical or no physical measures. For example, you take the same thing and you record where you've been, and you've all the time of your life, you spend almost near that repelling fixed point. So you come very close to that fixed point, you go away, you come even closer to this fixed point and spend a long time there, but this fixed point is sending you away, and you go away, and so on. So in fact, you spend all your life there to this point that hates you. And then there's the other possibility is there is actually no limit whatsoever. And again, there's a 1/n there. So my talk is about the opposite case. What are how frequent are good points? And the first thing I want to do is, everybody knows what is hyperbolic, but I just want to make a point that in the case of interval maps, the definition that you usually apply, that every periodic attractor has a critical point every critical point is the basin of a hyperbolic periodic attractor is not enough. For example, for me, this is a hyperbolic map. Of course, there will be a critical point in this basin, but it lives in the complex. So if I draw this, just here, there's this point, and you have this thing here, and there will be some critical point here that's in the basin of it. For me, that will be a hyperbolic map, but for most people, don't, in complex, that doesn't really exist. And that, of course, is, you can mimic this complex thing by negative Schwarzian, and well, that's the setting. So the result that I will explain in this talk, I'm going to put in this slide, but there will be various terms that are not going to be clear at this moment. And also, I'm not saying what precise assumption I have. But this is the kind of catch-line statement. So you have this real analytic family of real analytic maps. And then you assume it's also non-trivial. What does non-trivial mean? Well, I'll explain it later on in detail, but it basically means something happens. For example, it's not the case that one of the critical points always is mapped to a repelling fixed point, because then the dynamics for that critical point stays stationary. So it's kind of the opposite of what Laura was talking about in a sense. And so I'm going to explain the story, and I'm also explain a bit of the history of this theorem, because to my mind, this completes this story about hyperbolicity, at least in the real case. And okay, so let me come back to this later. So of course, the history of the density of hyperbolicity has a complex component from the Fatou conjecture. But I just want to mention that, in fact, even for real people, this has sort of been an old problem. For example, Smale asked this, and in fact, it was Guggenheim's PhD thesis. And then, of course, it was collapsed. But this is, it has a sort of long story that's sort of somewhat independent of the complex story. But, and that's why I want to sort of state it in this way, that this statement, if you take the space of CK maps, where K can be finite or it could be real analytic. This is what real analytic means. Ah, yes. So hyperbolic is, well, in the notion, in the smooth dynamical world, hyperbolic means that you have a decomposition of the non-wandering sets. And a part that's exponentially expanding. Well, of course, in general, you have a splitting, but we have no splitting because it's one-dimensional. So you have a hyperbolic part and a contracting part. Now, the special thing is in the one-dimensional case is that in the real analytic case, there will be only finitely many attractors possible. Because you can't have, well, for two reasons. One is that you know, that you can't have, let me draw that here. You can't have an infinite number of attracting like this, you know, goes infinitely many times for a real analytic map. So the number of attractors, this is meant to be homeomorphic or diffeomorphic. But they can only have a finite number. And there's another theorem, which is in the background of this, that you can't have that if you have a periodic orbit of sufficiently high period, it still will attract a critical point. And this is a non-trivial statement, which I didn't state here. But so this is the first definition. And the second definition, almost all points go to some hyperbolic attracting set. And the third definition is that all critical points are in basis of hyperbolic periodic attractors, which is the definition that you're probably familiar with. But my point is you should really add this if you're in the real world. Because you could have a parabolic point, for example, a point like this. So this would be a parabolic fixed point. And in fact, it could be the case that this has no critical point in its base. Of course, from the real point of view, there is no basin, but from the complex, well, you would have this, you know, well, let me draw the petals this way. So here you have this sort of critical point somewhere in the basin, in the complex. But in the real, of course, that doesn't exist. And so, you know, the technology that is in the background of this is, even if you have a polynomial, but you have some critical points on the real line and some in the complex, and with very, very complicated dynamics, maybe you want to remove those, prune those away. And so it's this is sort of in the background of this story. And so anyway, if we have it in the space of CK maps, hyperbolic maps are dense. And also there's a closing lemma, which is very famous in the smooth world, which means that if you take a recurrent point, could be any point, recurrent point, then you can change the map to make that point periodic. That's called the closing lemma. And that was proved in the C1 topology by Pugh in the, I think, 60s. And since then, there's essentially no progress in the you know, in the higher context. But in this case, yes, it works. And of course, it's one-dimensional, so it's a lot easier. Now, this statement, there's different versions of it, but let me kind of say it here. So in the quadratic case, of course, there were two papers or two developments or things, one by Krzysztof and Schwantek and one by Lubitsch at the same time. And they proved this statement here. But in fact, in the quadratic case, I just want to emphasize that there's a miracle, that 2 divided by 2 is equal to 1. And well, 2 comes from one thing, from degree 2, and 2 also comes from the fact that you have 2 children. So there is something, so if you, for example, take the family of maps set to the 4 plus a C, or something like this, this does not work, this proof. You really need different techniques. So that's, so I'm going to talk about the sort of history a little bit before I start the new theorem. Because I want to explain that even though the techniques will be somewhat used, it's sort of important to think why those techniques don't work in its full generality. I think, oh yeah, there is it. So the first thing that you should notice is that I talked about CK. And the natural thing when you have a CK perturbation is to do local perturbations. So you have a map, and if you have a smooth map, what you say is, well, and that's the idea of this Pugh lemma, and which is kind of famous, that you have some map, and you say, well, I don't like it. Well, I mean, this is a bad example, but so you have some map here, for example, and you say, well, I take some kind of neighborhood, and I can take a local perturbation with a bump function. And that, of course, is you know, and that is a clever trick that Pugh did very, very smart is you choose very carefully closest returns and choose these times very, very carefully. And then you can actually do these local perturbations. And this was also attempted in the interval case. And there are some developments, it was already going back to 71. There's the C1 version by Jacobsen. And yeah, Shen proved us in particular cases with bounded geometry. But in general, that didn't really work. And of course, there is also the Pallas conjecture, which is sort of saying that for almost all parameters, you have, some physical measures. These bad behaviors don't happen. And well, in the higher dimensional cases, there's a lot of people there, but they always work in the C1 topology, as far as I know. There's a statement, a counterexample to the, the original Pallas conjecture due to Pierre Berger. And in dimension 1, there is a number of results, but it's only in the unit critical case. And if you have several critical points, the techniques completely break down. And the reason that it breaks down is that the lambda lemma doesn't apply in higher dimensions. In some sense, all the setting, everything is ready. If you had a lambda lemma, you would be done. But that's not the case. So I'm going to then discuss this of a global approach. And this global approach, it goes through quasi-symmetry. And I don't think I need to explain it here, but I'm going to, let me first say, so what's the proof in the quadratic case? And this is sort of maybe useful. If FC is not hyperbolic and cannot be approximated by hyperbolic map, then in fact there always exists a maximal interval. And this maximal interval with C0 and C1, so that all these maps are topologically conjugate. And well, how does this follow? I mean, how does this hold? This follows from this property. So you have these two maps. So I'm now going to draw the parameter space rather than the dynamical space. So here I take here, and let me take C2 again to be real. I take two parameters, C1 and C2. And it turns out that, in fact, if you have these two parameters and suppose they are conjugate, C0 and C1, topological conjugate, that in fact all of these maps are conjugates, and in fact, as the statement says, there actually is a neighborhood in which it's conjugate, and which you get a contradiction, because you can take the biggest interval, which are where they are conjugates, and then you find a bigger set. So it is kind of an open-closed argument. If a set is closed and it's open, then it's everything. So the family would have to be trivial. In a sense, it would have to be. Now, the driving thing is two things. First, to show that these two maps are then quasi-symmetrically conjugate, and that's a deep theorem. And the second thing is the measurable Riemann mapping theorem. To say, well, if you have these quasi-symmetric, then you can play with this and make it quasi-conformal. And then if it works more, you can actually, take a path family in there. Now, what's quasi-symmetric? I think most of you will know, but if you have a homeomorphism, orientation-preserving homeomorphism, then you say, oops, then you say it's quasi-metric. There's too many plus t minus hx. This is less than k and bigger than 1 over k. So that means if you take a symmetric interval like this, then the image of one and the other one are comparable in length. So there's, of course, the quasi-conformal thing, which is sort of the same idea. And in fact, quasi-symmetric maps extend to quasi-conformal maps, and vice versa, quasi-conformal maps defined on a sufficient definite neighborhood of the real line are quasi-symmetric. So there's a strong relationship. So this is the, okay, so I'm going to just talk about it a bit more. So how do you prove that two things are quasi-symmetric? Well, I'm not going to talk about that, But the main tool there is sort of enhanced nest, and there is another, complex bounds. In the real case, you can prove these by hand. In the complex case, then you would use a lemma by Kahn and Lubitsch. In the real case, the proof is sort of, somewhat more tough in one way. If you accept the proof by Kahn and Lubitsch, which I do accept, then in fact, but it's complicated. That's what I'm saying. It's the depth gets displayed somewhere else, the complication. So it's the proof is delicate. So anyway, there's these two things. And so what does this tell you? Well, in fact, if you have two maps that are quasi-symmetrically conjugate, then you have rigidity. What does that mean? So if you have that F and G are quasi-symmetric, so there's a homeomorphism satisfy this property, then F and G are equal, and I probably should really say up to Möbius transformation, or normalized or something. So this is what I call rigidity. So you can improve this from this. So there is sort of two steps. Topologically conjugate means quasi-symmetrically conjugate means equal. So there's these things. And but this only works if all the critical points are in the real line. Because how would we know what happens in the complex if you talk about just conjugacy in the real line? The conjugacy here is just talked about in the real line. So you cannot really speak about whether the maps are equal or quasi-conformally conjugate. So this is really on the line, or on let's say R. So this is why here in the top line it says all critical points of the polynomial are real. That's a requirement for this statement. So that's one approach. And how to prove the density of hyperbolicity? Well, it's some kind of inductive step. And let me just kind of think. The first induction step is say, well, there exists an open set. There exists no open set without critical relations. Because if there was such an open set, all these maps would be topologically conjugate. But the topologically conjugate maps are quasi-symmetric conjugate and therefore equal. So you can't have an open set like this. And so this is the step that breaks down, even if you consider real polynomials that have also complex critical points. Because then there's no reason why these maps would have to be the same. The dynamics on the real line could be the same, and on the complex could be, whatever. You could, in one case, you could have some Siegel disk and the other something else, and, you wouldn't have any idea. And then there's some induction step and so on. But anyway, so this technique breaks down when you have non-real critical points, and also it breaks down if you have transcendental maps, and also breaks down if you have maps that are not globally defined. So in that sense, I think that it was not the. Now there's a second theorem and also a second paper that in some sense deals with this situation. And I'm going to try to explain why that proof also doesn't really do what we want. Because now let's take general real polynomials and drop the assumption about real critical points only. Then in fact, there's still density of hyperbolicity. But the tools are different. The tools are essentially different because what you do is, you make some special family, so what you actually do is you take a polynomial of, say, degree 2, you perturb it by something that has degree 1,000,000. Wow, 1,000,000, that's sort of quite different. But then you say, well, but you can actually use some straightening theorem to kind of make it, because these new critical points and so on are all far away. So you use some kind of polynomial-like structure and to, so I mean, I state here, first you take some smooth perturbation, you approximate this by a holomorphic map, but with a huge degree, and then you use some kind of, some straightening theorem to reduce the degree again. So it's a very indirect proof. It works, but in some sense, it's not useful for the thing we have. So if somebody tells you a family of trigonometric family or something, you couldn't use this because you're doing some perturbations that may break you completely outside this family. So that's why I think this is why by way of introduction, because in some sense you say, well, why would you do that? Well, let me be more formal now and state the setting. So the setting is the following. I'm taking real analytic maps with new critical points, and for simplicity, I fix the degrees. So I can maybe have the general critical points. That's fine, but for me it's easier to so this one maybe has a cubic, so inflection point 2, and here maybe 4, and so that's good. What I'm going to fix within my space. Now, of course, in hindsight or after the theorem, you can sort of glue different things. If 2 critical points coalesce and stay cubic, then you could do something. So, but I'm not going to really do it in this case. So this is the first thing. So that's the space of things. So that when I talk about real analytic maps, it's within this space. Now, the second thing is I'm going to talk about itineraries. Now, I think everybody knows that, but I'm going to just say that anyway. So if you have a point, it's sort of really what you, well, you have here some critical points. Let's say 3 critical points, and you record where you've been. So the critical point could be here, then maybe here, then maybe there, maybe twice, and then, and so on. So you keep a list of addresses. Of course, you could hit also a critical point, and then, you have this thing. So this is just a sequence of labels. And so that's the itinerary of a point. And so I call a family trivial if there exists a non-hyperbolic critical point. Now, I'm using a slightly unusual term. What's a hyperbolic critical point? It's simply a critical point that's in the basin of a hyperbolic periodic attractor. Makes sense. It's easier for me to use that terminology. So, of course, if you have a critical point that's in the basin of a periodic attractor, then the itinerary will not change. At least locally, it will not change. But anyway, so if you you say this family is trivial, if the itinerary of this critical point, non-hyperbolic critical point, is constant. So from a topological point of view, this point is boring, it's not doing anything. For example, it could map to a hyperbolic periodic repeller. So this would be an example of something where a critical point maps here and then stays in the same point forever. So that would be an example of this. But there's a second condition. There should be no persistent parabolic periodic point. And of course, in some sense, persistent parabolic point. So an example of that would be something like this. If you work it out, you see that the point square root of lambda is a fixed point, but also the derivative at that point is always 1. So, and it's quite a degenerate situation. So this situation, in some sense, is to show that it's quite degenerate. But here I state that it's persistent on an open subset. This parabolic point may actually just simply, for example, disappear. For example, if you take lambda here negative, in fact, you will get a bifurcation. This parabolic point will move to the complex, and from a real point of view, you don't see it. If you talk about an entire map and only real critical points, then you can say that this condition is can be replaced by that this has a parabolic fixed point for all parameters. Now, think about this. I mean, what I'm looking here is a huge slice through parameters, and not a local slice. J can be thought of as a big slice. So if you can check that the endpoints don't have parabolic points, you're good if you take this B prime condition. It's, you know, if the end of these things are kind of simple. For example, you only need to show that these two maps, they have different itineraries for the different critical points. And moreover, that one of them doesn't have parabolic things, at least in this setting. Here it's sort of slightly more tricky if you you know, don't have that assumption with negative Schwarzschild. And the reason is because this kind of thing doesn't apply, it doesn't have negative Schwarzschild. Or it has critical points in the complex that you know, you rule out in this you know, in this extra thing. Anyway, so that's for me a trivial thing. So sorry, maybe I didn't quite. It has nothing to do with the critical points. But you see, for me, a hyperbolic map, because I'm trying to show that maps are hyperbolic. If I have just one parabolic point and I stay away from that, then still the map is not hyperbolic. I mean, for example, you know, I mentioned already, you could easily have something, for example, you know, for you, it's always, you know, understood that the parabolic point will have a critical point in its basin. For me, it's not understood. If you have this point, it's repelling from both sides. So if I draw this on the real line, you have this parabolic point and you're moving away from it. And so I need to really put that in order to satisfy, well, Luna was talking about this definition of hyperbolicity. There is another version of this theorem, if I, you know, it's here. Let me see. No, this is the family. This is the second version. Yeah. No, first version. I wanted first to talk about this first version. So, if you take a family of real analytic maps, which also, moreover, depend real analytically on the parameter, and the parameter can be one-dimensional. In fact, you can take it more dimensional, but the one-dimensional result is stronger. You can take it, you can upgrade this to higher dimensional families. You know, with the parameter space higher dimensional. Then the set of hyperbolic maps is dense in this parameter space. Yeah. Well, no, of course it's not trivial. So for me, it's trivial because it's not doing anything. This critical point, for example, could be eventually periodic, and for all parameters. So dynamically trivial. Of course, the map is not trivial. That's absolutely true. So maybe you know, maybe there's a better term that I could or should use. But for me, trivial means that it's, you know, not as general as it should be. So yeah, this is just a terminology. But of course, all the time I should emphasize the critical points for me could be infinite. So the cardinality can be infinite. There's a second version which kind of relates to what Mitsu was asking. So if you take real analytic family as before, and now we weaken this assumption, so no critical point has the same itinerary for all lambda. Maybe I should say no non-hyperbolic critical points, and no non-hyperbolic critical points has the same itinerary for all lambda. Then, in fact, you can forget about parabolic. You just say the same hyperbolic maps are dense. So, the same hyperbolic is that I allow the existence of parabolic periodic points. I allow that, but every critical point should be in the basin of an attractor, hyperbolic or not. So, if, for example, I have well, let me leave it there. Yeah, so I mean, it could have this persistent, let me say that I could have this persistent parabolic point. And the critical point could just be in the basin here. For the whole family. And then I don't need to even talk about this parabolic property. All right. So one application that you can have is the following picture. So this is a family of cubic maps. And I take this picture from a paper by Milner. So if I take an analytic slice through here, or a straight line if you want, what I claim is that you have density of hyperbolicity in that slice, in that one parameter, real one parameter direction. Previously, you could say, well, the parameters where you have hyperbolicity is dense. But for all you know that if you take a straight line, you're going to avoid that dense set. It's not clear at all that you would avoid this. Okay, so I'm going to outline the proof a little bit. Let me just check because I have lost a little bit sense of time. So what am I? Okay, perfect. And maybe I will even not use it. Perfect. So so the sketch is sort of three steps. And I'm going to sketch them not in detail, but I'm going to just the stretch of the strategy of the proof. There's a theorem A, which works by contradiction. It says if hyperbolicity were not to be dense, then there exists a small subset of this parameter space and non-hyperbolic critical points. You know, this didn't fit on non-hyperbolic critical points with a constant itinerary or needing invariant. And so one way of putting it is trivial, you can upgrade to locally trivial. You know, so non-hyperbolic maps has to be locally trivial. So yeah. Yeah, so in fact, that could be, and that's, of course, these are, you know, if they're diffeomorphs on the real line, then well, what happens? You know, you basically are in a very simple situation. You can have a few fixed points or something. So it's a sort of the straightforward case, which I kind of skip, but you're totally right. You should really mention that. Yeah, no, you're totally right. If you have no critical points, then, you know, we are in some sense good. This is the hyperbolic language from, you know, I guess from the old days. Now, so what I have done here now is, in the first step, if a family was not trivial, so not then if you had no density of hyperbolicity, then there is a subset, and I'm going to draw schematically this thing. And there's a subset here where nothing changes for some critical point. Now, theorem B says, well, actually, there is and I'm going to draw this like this. There is some kind of analytic manifold, which I'm going to draw. And you know that this curve kind of sits inside that thing, at least locally. This is the identity theorem, right? If you're locally in there, you're there all the time. Except this manifold has boundary. These are maps with parabolic points. So you could drop out of this manifold. This is a real analytic infinite dimensional manifold. Remember, these are, you know, I'm talking about real analytic things, so the dimensions are much higher. But there is a sort of a statement, D says, well, actually, this manifold is not smooth or analytic near the boundary. There's some curling going on. So that is sort of the final step. So your real analytic thing actually could never reach the boundary. And then, you know, you get the statement of this theorem. So the proof is sort of, you know, those steps. And I'm going to try to discuss all these steps a little bit. So the strategy of the proof, I think, is sort of, quite clean. And of course, some of the previous results will feed into this, but I'm going to start with the first statement. And well, here we said, suppose there is a subset, there's an interval. What am I saying? I'm just always changing so that this is probably not what I wanted to say. So there's no dense subset in this subset where it's hyperbolic. So let me state it correctly. I think so the statement is there exists no a dense subset in J, and let's call this D, so that F lambda lambda in D implies F lambda is hyperbolic. This is what I should have written there. So there is an open subset where you don't have hyperbolicity. Then, in fact, there is an even possibly smaller subset, so that the itinerary will actually have to be constant for that. So this is really what I mean. So if you don't have hyperbolicity sufficiently often, then you can find yourself a small interval in parameters, so that within this thing, the itinerary of some critical point, some non-hyperbolic critical point is the same for all lambda. So this is kind of the trivial statement that I really wanted to, because I want to argue, suppose you have non-density of hyperbolicity, then I want to have locally something where there's a critical point that's boring, what I call, trivial locally. In fact, there is another version. This you can think of a version of the statement of a famous theorem of McMullen, which says if you take a family of rational maps, then the open quasi-conformal conjugate classes form an open set. So what does this mean? So you're talking about the set of rational maps, which is of course different in my case. And now you're looking at the ones that are structurally stable. I mean, these are maps which are conjugate, in fact, quasi-conformally conjugate, but forget about that statement here, because that's going to be automatic. They're conjugate. And it says that, these sets where they're conjugate, locally conjugate, are open. So you have these maps that are structurally stable in this space. And this forms a dense subset. Now, just to kind of translate this, there's two ways in this can be. One is what you would call a queer component, which of course they don't rule out. And the other one is that you have actually a hyperbolic map. So, a dense set, yes, open dense, yeah. So this is sort of the analog of this statement, but of course the proof here relies very heavily on the lambda lemma. The lambda lemma is talking about some kind of a tool in complex dynamics, and of course we don't have that tool here. So the proof has to be different, and the proof is actually it uses just real tools. It's not, it took me a long time to work out how to do it, but in fact, in hindsight, it's quite easy. The main tool is absence of bonding intervals, which is the analog of absence of bonding domains, but you also have sort of a little bit more information about the intermediate value theorem in the real line. So it's kind of elementary, but not easy to prove. But this is the first ingredient. So this is sort of telling me that I have this little parameter subset J prime in J, and all the maps there are going to be kind of, at least this critical point, dynamically, they're all the same. from that critical point on. All these critical points have the same dynamic. And that, of course, they can be infinite or not, but that's the story. Right, so this is the first step. So now we have this local thing. So the second step is, I'm going to just make an easy case, a trivial case first. Suppose you have a small subset where the critical point is, for example, eventually periodic, or periodic. Here should be periodic or pre-periodic. So suppose you have this sort of relationship. Was an open set of parameters. Well, then it holds for all lambdas, right? Just by the identity theorem. So, in fact, if it's true locally, for some subset, then it's true for all lambda. And of course, this you could have that this lands on a periodic point, and the periodic point bifurcates and all that. It's not relevant. You just look at this statement here in this way, and it's, that persists for all lambda then. And so, okay, so this is the easy case where it's sort of a finite orbit. Now, so suppose there is, this statement, and I'm going to just state it now what we want to argue. This is what I call theorem B, but in fact, there's two steps in this, two arguments in here. Suppose there is this small subset. So this itinerary has a constant itinerary of this CI, this non-hyperbolic critical point is the same all the time. And let me just for the moment, because this sort of is a separate argument, also assume that the point doesn't accumulate on the parabolic point. Remember, again, this is something that complex people don't have to worry about, but you may have a parabolic point, and you come very close to here, you go away, you come even closer to here, and this parabolic point, of course, is bothersome. There's all kinds of things you cannot do with that. But anyway, so for that we need sort of a different argument. So this is this statement that in fact the itinerary is the same. And this theorem follows from something that is actually much more abstract, and that's something that was I did with Trevor Clark. And again, you're talking about this space A nu. And now all maps here are topological conjugate to F. And let's also add in that all periodic points of F and G are hyperbolic. So I can have parabolic point, so attracting hyperbolic points. I can have repelling, but I don't want parabolic points. Well, in that case, this space conjugacy class forms this real analytic manifold. This is a subspace of this infinite dimensional space. In fact, if you fix the domain of this thing, this will be even a real analytic Banach manifold. Otherwise, it's something slightly more subtle. And the codimension of this space is equal to, well, I mean, the number of critical points minus the number of critical points that are in bases. Of course, this is because I talk about topological conjugates. So I don't need to worry about multipliers and so on because they're topological conjugates. If I fix the multipliers, then in fact you didn't get that. So there's a version of this. So this is this statement is Mitsu, you look like you are going to ask a question. Okay. No, sorry, but maybe I will talk then. And so remember, the critical points can have infinite orbits here. So that's quite different from the story that people usually in the complex world are looking at, where critical points are finite. For example, Laura's talk is always where the critical orbits have, or at least some critical relation. And the final statement is, in fact, this space is connected, path connected, and in fact, I wanted to add here also contractible. In fact, it's contractible. So, so let me kind of make a statement here also. So it's easy to think of some map. So even in the space of polynomials, I'm just writing here something because let me, I don't know why I'm writing this, but it takes some sort of degree. And suppose on the real line, these are unimodal maps. Then you will actually have plenty of maps of this type, which have the same itinerary. For example, even the critical point could be eventually periodic. So this is not, 1 point, but this would be a whole, much bigger space. So within this space, it would be path connected. When I say within this space, I lie, not within this space. I have to go outside my space because I need to have a connection of real analytic maps. So I can connect them by path connected by, real analytic family, these two polynomials, but I don't necessarily know that I'm within my space, sadly. Of course, I would like to know that because, that's, but yeah, so this is actually a contractible space. And in fact, this statement that I had was something where you have a global assumption. So I'm going to state this just to say, well, suppose I have a more local statement. So some critical points changes itinerary, but others, their itinerary keeps the same. I need to apply it to a setting like that. Because remember, in my theorem A, I only produced possibly only one critical point whose itinerary is constant. So I don't necessarily know that, so I can't say that some statement like that within the family, for some critical point, this is going to, but I know it for some. So let me say the following. So suppose you have some kind of compatibility condition that I'm looking at a collection of critical points that are kind of related. And by related, I mean if one critical point is in the omega limit set of another critical point, so it really accumulates, then I want this set to be this critical point in that set. So that's sort of a coherent collection. If I then say all the critical points, every periodic point in the omega limit set of this is going to be hyperbolic. That's another assumption. Then I'm saying I'm looking at the maps where the itineraries are the same for those critical points. So this is not for all critical points, but only for those specified critical points. Then this space is a real analytic manifold. That's precisely what I need. So that's my kind of second thing, that I have this infinite dimensional real analytic manifold, and you're locally inside this analytic manifold. So what I need to do is I need to kind of upgrade the previous theorem to kind of localize it. Some critical points don't play a role anymore, so I'm going to do some stuff. I'm going to look at something which is piecewise defined, and then prove some similar statements. And the final ingredient is the following: is that suppose there is a closed interval, and the critical point has always the same itinerary. Well, there's several ways of saying it, but let me put it this way. If for some point in this parameter space, the periodic points in this omega set are all hyperbolic, then they stay always hyperbolic. Or another way of stating is that the boundary of this space is actually not going to be sufficiently smooth. You cannot reach a boundary with a real analytic manifold. So you have this real analytic family, and it just can't reach the boundary because at that point the map is just I'm going to destroy this schematically, but it's kind of curl up. He says the parabolic thing, this is an infinite dimensional thing, and so you need to show that this real analytic thing can't reach there. And so then you show that in fact the map is really trivial globally for all parameters. Okay, so that's what I want to say. So this is a slightly different world, of course, real analytic, but I think the tools are really from complex dynamics. And the main tool, which I maybe just say one word about, if that's okay, well, am I still okay? Okay, so I'm going to write this, I'm using prune polynomial-like. And prunes, everybody knows what's polynomial-like, but it's prunes. So you have a structure, and in fact, I have a prune Julia set. So if I have a real analytic map, so from R to R, I'm going to assign some Julia set to it, but it's some kind of truncated. The map, of course, is not analytic on a huge neighborhood of your interval, maybe. So I'm going to define some geometric object, which I call prune Julia set. And that will be kind of one of the ingredients, which I think should have more general applications. And so that's the tool that is used in this thing about this real analytic manifolds. Yes, there is. Yeah, that's absolutely right. So since the map is, yeah, thank you. Since the map is real analytic, there's a neighborhood on which the map is complex analytic. I don't know how big, but for example, well, if you take the preimage of this real line, which is invariant, forward invariant, backward invariant, you would like to draw it like this. But it's not in the domain of a definition. So you do something, and that's what is called a pruned Julia set. So this is sort of essentially kind of cutting away all the nasty stuff in the complex. So for a real guy, which, you know, I grew up in the, I'm almost complex already, but but it grew up in the real, of course, this is something, you know, like heaven, that you can, all the stuff that you don't really want to study, you can remove from your consideration. Thank you very much.
Very much. So a couple of very quick questions.
Gustavo.
So thanks for the very nice talk. Do you know how to relate the dimension of this new locally defined real analytic manifold to the one of the previous one that we had that was defined using sort of all critical points?
Yeah, I think I do, because but in a space that I need to really would need to tell you, which I kind of skipped, because I'm going to take instead of the interval, I'm going to take a finite union of intervals.
Mm-hmm.
And the map is not going to map this interval to another interval, but, you know, map into the R. So I'm looking at the points that survive this, you know, stay in the union of these intervals.
Mm-hmm. And
if I look at this kind of space, so my space of real analytic maps will change a little bit. Then the codimension is going to be the same, namely the
mm-hmm. Thanks.
In a classical proof for a quasi-symmetric rigidity, Sullivan used the open and closed argument.
Yes.
So that the topological conjugacy set is like an open and closed interval.
Exactly.
Using a QC deformation.
Yeah.
And here the theorem D looks like you're saying the similar things. So for closed interval, you get similar dynamics all the way to the end.
That's right. In some sense, where is it? In some sense, it's sort of a similar statement, but the argument is a bit, the way you prove it is different.
So you don't go via quasi-symmetric conjugacies,
Yeah,
or
rigidity? Of course I mean, actually this theorem, I only know how to prove it from, you know, using some statement like this. That's the only way I know how to prove it. So I show you have this in this real analytic manifold locally, and then you're kind of globally. So of course so that's the only way I know how to prove that. And of course, just to kind of answer that more fully, this open-closed argument is precisely what was it here? What is kind of used on this page, right? This is precisely the argument. But even in the case where you have more critical points, you need to kind of you do it by dimension. You need some induction. So every time you say, well, there must be at least one critical relation, otherwise you get context. So you look at the space with one critical relation, and then you do inductively. So that works in that case, but only because you have rigidity within that space. So I mean, if things are QS conjugate, then they're actually equal. And this, of course, is part also of the open-closed argument. That if two things are quasi-symmetric, then afterwards, in the benefit of hindsight, you could say, well, they must have been equal. Because that's what this argument really shows. If two maps are, unless they're hyperbolic, but if you had two topological conjugate quadratic maps.
But the new approach doesn't use this rigidity result?
Absolutely. Of course, this theorem, of course, is precisely used as, our quasi-symmetric rigidity result. Of course.
In theorem A?
No, sorry, theorem
D?
C.
C. Oh.
No, I mean, this is building on that language. But it's sort of stronger because, well, I mean, in a sense, the proof is kind of, you have two maps and you need to show that you do quasi-formal deformations. So this is how the family goes. And then to show, that you need to show that this is actually a manifold. The space is parameterized by quasi-formal deformations.
But it doesn't show that it's a manifold at the boundary.
No. And also a priori it doesn't show, well, path connected is easy, but to actually have contractible is something more difficult. But that's the language, and the dimension is subtle. That's more subtle because you need to, you need to work out what's the tangent space. And for that is the kind of the language of horizontal and vertical vector fields, which is, what Lubitsch uses very heavily. And so I'm not going to explain, but this theorem it has an analog in the unicritical case, but their proof has to be different. Because what they use there is you have some hyperbolic things, which kind of, and they use a lamination, sort of a lambda lemma to get the manifold structure by density, by exhausting this. So that's a lambda lemma approach. Sorry, I answered that a bit long, but
thank you.
Thank you very much.
Thank you. Okay, so let's thank Sebastian again. It's a super pleasure for me to introduce the last talk of the morning. So this will be by Krzysztof Baranski from the University of Warsaw. And he will be talking about from cubic Newton maps to cubic polynomial, a tour of Mandelbrot sets.
Thank you very much. Well, first, I would like to thank Anna and all the organizers for the invitation. It's a pleasure to be here. Pisa is a very nice place, and when you are here and when you are leaving, you have a feeling that you should return. And in fact, that's exactly happened to me, because 5 years ago, together with Nuria Farzeja, Czawę Żarkę, and Bogusia Karpińska, I was here at Centro di Giorgi within a research in Paris program. We started some paper, but then we left Pisa. It was hard to work together. There was COVID time and so on. And when I heard about this conference, I realized that I must return here to finish this paper. Okay, so I was wondering what to talk about, and I had a bit of problem because the conference is on the parameter space, and the only work I did on parameter spaces was my PhD thesis, some 25 years ago. But fortunately or unfortunately, these papers are almost unknown, so it is safe to talk about them now. So these are these 3 papers, and another problem is that these main ones are very long, some 50 pages long each, full of technical details. So during this talk, I will just explain the results and show a lot of pictures, and well, brave enough people can go in the details in the paper by themselves. Okay, so what is the motivation for this work? There are 2 old papers. The first one in Communications in Mathematical Physics in 1983 by James Curry, Lucy Garnett, and Dennis Sullivan, where they described a space of cubic Newton maps, and they realized that there are some sets similar to the Mandelbrot set there. So what's the cubic Newton map? So a cubic Newton method for used for finding roots of cubic polynomials is, as you all know, defined by n of z is z minus g of z over g prime of z, and g is cubic polynomial. Well, and since we will be continuously changing the coordinates by a Newton map, I mean cubic Newton map. I mean a map which is conformally conjugated to a Newton method. And it is easy to check that this is equivalent to say that there are 3 supersinks. Three super attracting fixed points. Okay, so these are cubic Newton maps. And there was another paper in Acta Mathematica by Bodil Branner and John Hubbard in 1992. This was the part of the study of the space of the structure of the space of cubic polynomials, which appears to be very complicated. And in this work, they described many Mandelbrot-like sets, which are quasi-conformally homomorphic to the standard Mandelbrot set, which are contained in this in some one-dimensional slices of the two-dimensional space of cubic polynomials. Okay, so at this time I was a PhD student. My supervisor was Felix Przytycki, which is I'm very glad that he's here. Who asked the question? He asked a question: can one connect these Mandelbrot-like sets in a cubic Newton maps and cubic polynomials by some continuous path of Mandelbrot-like sets joining one and the other within some family which contains both of these families. So when your supervisor asks a question, you should try to answer it. So I started to think about it. Well, a natural candidate for the space is the family of cubic rational maps with two super attracting fixed points. Yes, because it contains both cubic Newton maps and cubic polynomials. Okay, and it is two complex dimensional. Okay. Okay, so we have these two superthings, C1 and C2. We can put them at 0 at infinity, and also put the third critical point at 1 by a conformal change of coordinates. Of course, this excludes one special case, that these 3 critical points are the same one, which is just the case of the polynomial z square. Okay, z cube. Okay, so we have the family F, calligraphic F, which is exactly the family with 0 and infinity as superthings at the third critical point at 1. So one can write a parameterization of this family. It's written here. It's not so important, the precise formula. We have these 3 critical points, and the third one is denoted by U all the time. You can see that it depends on one parameter B, and the second parameter is just the critical value corresponding to 1. So it is quite a nice parameterization. So we will be working. We will be studying this family, and as you know, as you have heard in Laura's talk, well, the structure of this such families are generally complicated, and what one tries to do is to study some one-dimensional complex slices of the space, because then you can try to prove something. So that's exactly what we will be doing here. But first we will have a short look at the moduli space. That is the space of holomorphic conjugacy classes of the maps from F. Of course, this is the quotient space under the action of Mobius map with exchange these points 0, infinity, 1, and U. Okay, so it appears that this moduli space is homomorphic to some algebraic set X in C3. Well, except one point V. This point V corresponds to this omitted polynomial Z cube. Okay, that's because of this parameterization. I can maybe. Yeah, here we assume that well, 1 is not 0 nor infinity, so this is excluded, and this is this point. So a part of this is an algebraic set of complex dimension 2, and this is not a manifold. It is an orbifold, and it has exactly it has singularities at points corresponding to Newton maps. It has some pinchings there. Okay, so we start to study this one-dimensional complex slices of this family. And as a model slice, we take here the family F2, which is defined by the condition that this critical point 1 is periodic with period 2. So this is This is the simplest well behavior outside the Newton maps. Well, the third critical point is periodic with some period, minimal, larger than one. Okay, this gives us some one parameter family, which is conveniently parameterized by some parameter lambda. Lambda is in C bar minus 10 singular parameters, where the map degenerates to some lower degree map. Okay, and this is the parameter space of this family. So here in all the pictures there will be 4 colors. The color blue corresponds to the basin of 0, the color white the basin of infinity, the color black the basin of 1, and some different behavior will be denoted by yellow. So you can see we have several components. So in this family, we have prescribed behavior of 0, which is fixed, infinity is fixed, and 1 is periodic with period 2. And there is the 4th point, u, is free, and it can be in the basin of one of these 3 points. So, for instance, here in the black region, it is u is in the basin of 1, here is in the basin of 0, and so on. Here, infinity is not a singular parameter; it's a regular parameter, and you have this singular parameter somewhere here. It's not important at this moment. Other parameters, lambda, are not singular; just indicate the centers of these components. Okay, so this is a nice picture, and we will try to describe some of behavior corresponding to this. Okay, so in 1996, Felix Przytycki defined a notion of exotic basins. So what is an exotic basin? Suppose we have a rational map F of degree at least 3 with an attracting fixed point S, and B of S will be always here an immediate basin of attraction to S. So B of S is called exotic if there are 3 conditions. Oh, sorry. First, B is completely invariant, which is equivalent to say that F has a maximal degree D on B of S. Secondly, B is not non-simply connected and contains less than D critical points counted with multiplicity. This is a definition. Why it is called exotic? Because in many cases it cannot appear. For instance, well, first, quadratic rational maps cannot have exotic basins because, if the degree is 2, then no, if the degree is 2 and the basin contains less than 2 critical points, it contains just 1 critical point, and then it is simply connected necessarily. Secondly, a remark is that if B is simply connected, then it contains exactly the number of critical points counted with multiplicity is exactly the degree on the basin minus 1, because then if the basin is simply connected, the map is conjugated to a Blaschke product on the disk, and so the number of critical points is exactly like this. And note that the basin of infinity for polynomials cannot be exotic, because then infinity is already a critical point of degree d minus 1. So if it is exotic, then it cannot contain any other critical points, which means that it cannot be, it must be simply connected. Okay. So in one of these papers which I mentioned, yes, please. No?
I hope that I proved that if that exotic cannot exist, that the number of critical points, if the basin is not simply connected, must be bigger. It must be at least degree. So more than if it is simply connected. But it is even written in the same paper. I prove it. That basins for Newton method, basins of the attracting fixed points are simply connected. The first part of the paper is correct, but the second part, where I prove it exotic cannot exist, is wrong. And then I found this possibility, and Krzysztof continued this topic.
Thank you.
Okay, so we have the following result. If we have a rational map of degree at least 3, and if we know that the immediate basin of attraction of an interacting fixed point S contains at least 2d minus 4 critical points, which is all but 2. Critical points or critical values. It is the same. Then F has maximal degree on B of S, which means that the basin is completely invariant. And the result is sharp in the sense that for any smaller number of critical points counted with multiplicity, one can construct by a quasi-conformal surgery, for instance, an example of the basin. Yeah, probably. Okay. Thank you. Okay, so what it means for our family of maps F2. When you read this in this situation, which is very simple because we know the behavior of these critical points, it just means that okay, we have this free critical point U, and if it is not in the basin of 0 or infinity, then of course this basin of 0 infinity must be simply connected with degree 2 because it contains only one critical point, this supersync itself. And if U is in one of these basins, then the map has maximal degree, and the condition of being exotic is just equivalent to being non-simply connected. So in our case, we can say that the basin is exotic if it is not simply connected, and non-exotic or regular if it is simply connected. Okay, well, since so suppose well, here is we denote, so lambda is the parameter space for this family. Lambda zeta is are the set of parameters where this free critical point is in the basin of immediate basin of zeta. So if it is, if you have a parameter from this set, then we know that f is hyperbolic, structure is stable, and it means that either it is exotic for all the parameters in the component of this set, or non-exotic for all the parameters. So we will call this parameter components exotic ones or regular ones. And just recall that it just means that that the basin is simply connected or non-simply connected. And we can just classify these components in this family, in this picture. It appears that there are exactly 4 components of lambda 0 and 4 components of lambda infinity. These are symmetric situation. 3 components are regular. 1 is exotic, and there are also 3 components of lambda 1, which means that U is in the basin of 1, and 4 components of where U is in the basin of immediate basin of f of 1. Remember that 1 is 2 periodic. All regular components are topological disk in the parameter space, which means that they have the center. At the center, this critical point U is just equal to this supersync. And exotic ones are puncture disks. And in the center, there's a singular parameter where you go outside the family. So this is a magnification of the previous picture. You see these regular and exotic components. These regular are denoted by R, exotic by E, and you can see these yellow regions, which are similar to Mandelbrot sets. And in the center, there are Newton maps. There are 4 of them. Of course, there are some symmetries, but it's nicer to write it like here. And what we are going to study, we are going to study away from this parameter to these 2 components, the blue one and the white. I will explain what I mean. First, we should look at the combinatorics of cubic Newton maps, and this is due to many results. Well, some people are present here. So we have suppose we have a Newton map with supersync 0 U at infinity. Okay, the third point, 1 cannot be a supersync. Okay? And the fourth. Okay, so here it's more general results. So we can go outside this F2 class. We just assume that 1 is not in the basins of supersync. It can be periodic with period 2 or do other things. So what we know? So first, we know that the boundary of the basin of supersinks are Jordan curves. And well, I think in 1989, Felix proved that these basins are simply connected. Then Mitsushi Shikura proved that the whole Julia set is connected. And in fact, these boundaries are Jordan curves. and the map on the basins is well, since one is outside this basin, the map is just conjugate to z square. Okay, if it is conjugate to z square, then we can define internal rays. Okay, we have this basin of supersync. It is conjugated to z square. So we can define interior rays. This is angle theta, so we call it r zeta of theta. And since the boundaries are Jordan curves, they have well-defined landing points, which we denote by L zeta of theta. Okay, and theta is from 0, 1, not 0 to pi, but 0, 1. Okay, so what we know? We know that well, we can, after possible exchanges of 0 at infinity, when we look at the common, the intersection of the boundaries. So we have the intersection of boundary of the basin of U and 0 is just 1 point, and the other with infinity is infinite, and in fact it is in invariant counter set. If we exchange infinity with 0, the situation exchanges. Next, the set of angles, for which where the landing points of internal rays of angle theta in the basin of U and infinity are equal, it is away from 0. It is the minimum of this infimum of this set is called Head's angle. This was showed in the unpublished PhD proof of Jane Head. Okay, and in fact, it is these common landing points are exactly the whole intersection of the boundary. And the last thing, the critical point 1 is not equal to the landing point of internal ray of angle of Head's angle, if and only if this angle is periodic. And maybe I will explain it on the picture. You have 3 basins: 0, U, 0 at infinity. This is a non-standard way of looking at Newton maps, because in this standard parameterization, this is infinity. Okay, this is a repelling fixed point, the common landing point of 3 rays of angle 0. And here at infinity we have a supersync. Okay, so you can see that basin of U have just one common point, the boundary, with the boundary of the basin of 0, and many common points with the basin of infinity. And this is this head angle, 1/3. So here we have not intersection. And here a counter set of angles at which we have intersection of these 2 basins. Okay, and it can happen that 1 is this point, Okay, and this was this condition exactly when it is okay, and if it is not the case, then it means that this Hertz angle is periodic, and in fact, in our family F2, it is always 1/3. Okay, so this is the combinatorics, and now maybe I will skip it and explain it on the picture. So the theorem is the following. We have another magnification of the parameter space of F2. We have Newton maps, a Newton map here, and we prove that there is a curve in parameter space going which ends at the parabolic parameter. In this parabolic parameter, we have a parabolic point with multiplier 1. And U, here U is fixed, it's a supersink. And along this curve, U is in the basin of a attracting fixed point of multiplier T, where T changes from 0 to 1. And here U is in the parabolic basin. And then we have a bifurcation of curves. We can go into the region where U is in the basin of 0, and it is a regular basin, a non-exotic one. And it can also jump into the basin of infinity, which is exotic. So it is just written here as a theorem. And the important thing is that if we are at this regular component, parameter components where U is in the basin of 0, then we can go further with this curve to just to the parameter when U is equal to 0. This is the center of this hyperbolic component, and then the map is conformally conjugated to a cubic polynomial. Well, it should be infinity, not 0, but the figures looks nicer if they are drawn in that way. So we have formally, we have not a polynomial, but a map conjugated to a polynomial. We should exchange 0 at infinity, and we get the polynomial. So we have the first step in our tour from Newton maps to polynomials. Okay, so this is the theorem. And now there are pictures. So this is the starting point. U is fixed. It is a supersink. And then we change continuously the parameter by some quasi-conformal surgery procedure. And U then is in some attracting basin of some point which is different from 0 or infinity. And this has a limit, this parabolic map. So now P is a parabolic fixed point with multiplier 1, and U is converging to this point. And now we have this bifurcation. So here, this is a non-exotic, no, this is an exotic case. So U jumps into the basin of infinity, and you can see that this basin is non-simply connected. It is exotic, yes. And the second possibility is that U jumps into a non-exotic basin of 0. You can see that it is simply connected. Yes, and then we can go further, modify the parameter so that U is just equal to 0. Okay, this is the case, and in fact this is just a polynomial, but we are looking from infinity, so we can change the coordinates, and it is the Julia set of a cubic polynomial with a supersink 0 and critical point 1 of period 2. So this is this bifurcation. How much time do we have? 15 minutes, almost, no. Good. So now we are going to describe this continuous path of the whole Mandelbrot-like sets in the family F, going outside this F2. So we use here machinery by Douady and Hubbard on quadratic-like maps, or polynomial-like maps in general. So a quadratic-like map is a proper map of degree 2 from some topological disk U into larger disk V, and we look at points which are all the time in U, and they form field in Julia set K, KF. And we know that every such map is conjugate, quasi-conformally conjugate to real actual quadratic map, quadratic polynomial by a quasi-conformal homomorphism, which is conformal almost everywhere on this field in Julia set. And this parameter C is uniquely determined if this set K of F is connected, and then the C is in the standard Mandelbrot set. Okay, so it means that if we have a family of quadratic-like maps parameterized by some sigma, we can define a function chi from this parameter set, where chi of sigma is the C for sigma such that this set filled in Julia set is connected, which means that C is in the Mandelbrot set. And now, if you have an analytic family of quadratic-like maps, I won't define it precisely. What is an analytic family? It's a good one family, parameterized by some topological disk. If we assume that this set of parameters where the map is conjugated to a quadratic polynomial with parameters in the Mandelbrot set, if it is compact within this set of parameters, then we can look. So we have this family U, and we have this set where we know that the map is conjugated to a map, a quadratic polynomial from the Mandelbrot set. Then, if we take this parameter, for sure, we have omega sigma is the critical point. It cannot be, of course, it cannot be fixed. So, because then the map would be conjugate to Z square. Sorry. Okay, we assume that this set that this set is compactly contained in the set of parameters, and we take some curve surrounding it, and on this curve we know that the critical point cannot be fixed because we are not in this set. So we have some vector which is non-zero. We can normalize it, and if we go around this curve, this vector go around the unit circle, say after normalization. And if it goes once around the unit circle, then this chi is a homeomorphism. And then this set, this set is in fact quasi conformally homomorphic to the standard Mandelbrot set, and we call it Mandelbrot-like family. Okay, so now we are now outside this family F2. We are just in family F, which means that we have super things at 0 at infinity. And now we start from Newton maps. And suppose we have a Mandelbrot-like family in these Newton maps, which exists by this old Carr, Garnet, Sullivan paper. Okay, so we suppose that, well, the picture is more or less like previously. This assumption, which I won't discuss now. And now we have a long theorem, again, which can be described shortly in this way. We have this Mandelbrot-like family in Newton maps, and then we can make a continuous path of this, which ends at parabolic maps, and then bifurcates into two paths. One is where U is in the basin of infinity. This is an exotic path, which has no limit general. And this other path, when U is in the basin of 0, is it is non-exotic case, and it ends at the map where U is 0, which is these are map conjugated to polynomials, cubic polynomials. And these are the pictures. This is an initial family of Newton maps. Here you have a Mandelbrot-like set. Then we can deform it to parabolic one. Yeah, and you see that as usual, this parameter space resembles this dynamical space. This very beautiful phenomenon, which is far from being described precisely. Okay, and now we have these two paths. This is the exotic one, and you see that also the parameter space is here. The parameter component, this white one, is not simply connected, and this is non-exotic, and we can go further to arrive at maps conjugated to polynomials. And these are Mandelbrot-like sets described in the paper of Branner and Hubbard. Well, and the last thing is just about the proof. So you can just define this good family of quadratic-like maps by using this combinatorics, as you can see. And the hard thing is to prove that this has a limit when going to this parabolic parameter, which is written here. So and then you can perturb it a bit and show this bifurcation. So thank you very much for your attention.
So this PhD started from an innocent question. What happens if a critical point additional in basin of attraction converges to the boundary through a parabolic point? So this topic was popular then. It is still difficult and popular. And Krzysztof in place of doing a general theory, he just elaborated such beautiful examples. And another remark is that my paper where I found counterexamples, I don't remember the title precisely, but part of the title is in which hyperbolic component contains polynomials, when I already knew that not every hyperbolic component contains polynomials. Yeah, that's that.
Thank you, Felix. So there is another, okay. Dirk.
So you mentioned that this goes back to your thesis, which is quite a while back. So often in,
Yes, yes.
excused. So question, in hindsight, we often get, well, if we write a thesis and in hindsight, we reflect upon and realize what we should have done in our thesis back then. So question, do you have any wisdom in the time since then that you'd like to share beyond what you've done in your thesis?
Well, in fact, I have not been working on it. I leave it for the community.
Okay.
So there was another question here.
So what is the relation between the Mandelbrot-like set in the cubic Newton map and the cubic polynomials? I mean, are they dynamically related when you pass along the path that you construct?
Yeah. So if you go along this path, everything is well. Yeah, you have a continuous family of these conjugations. So it is a general theory of Odwadi and Hubbard. So once you know that this path exists, you have these conjugations.
When I made my pictures in this paper about hyperbolic components, I saw that similar pictures are in papers by Macmillan or related to Macmillan of maps of type Z in the power G plus 1 over Z in power P, these Julia sets consisting of circles, that if I open these circles a little bit, then the whole complement of Julia set is just basin of attraction to one point. And we obtain examples which are in my papers. So both somehow are related by that. I have just one basin. I just have Julia, which is Cantor. Look at pictures. They are not so different.
Loci as shadows of Julia sets.
Thank you. So first of all, I would like to thank the organizer for this conference, for inviting me here when I was still in France. It's a real pleasure to be back here, especially since it was in this room that I gave one of my first talks a number of years ago now, and to see again some of the same people that were in the room at that point here now. Since the talk was in parameter space and bifurcations, I will have also the occasion to mention the result of which I talked about that time, again this time. But I will talk about something different. So, just to set some notation. So, the general goal of this talk is to at least convince that there is a way to study dynamical spaces and parameter spaces as sites of the same objects, okay? In order that we can use dynamical tools, and by dynamical I mean tools adapted of phase space, in order to study parameter spaces. Now, just to set the context, if we take a rational map, I will usually denote by C hat or P1, the Riemann sphere. We can partition this in a Fatus set and in a Julia set. And in this setting, if now I take lambda, which is a parameter space, which is a complex manifold, I can partition it as a stability locus and a bifurcation locus. This partition comes from essentially the 80s, from the work of Magnus et Sullivan and Lubitsch. As was already mentioned, around the year 2000, Laura De Marco introduced a current who's supported precisely here. And in order to introduce it, let me say that one of the possible definitions of the Julia set is the support of the unique measure of maximal entropy. Also a result by Lubitsch, and a number of properties has been studied by Brolin, Lubitsch, and Freire, Lopez-Magnier. Now here, this is the support of TBIF, which is a current, the bifurcation current. Now, the point here, and you will allow me for being a bit imprecise during my talk, I will always assume that I have dimension 1 in parameter space in order to have this current here actually to be a measure. This, of course, is not always the case, but I will mainly talk about one parameter families in order not to have this small problem with to talk with current. So I will talk about measure. Of course, as was mentioned before, actually studying what is the measure in the general setting is a complicated problem, already studied by Bassanelli-Berthelot, Dujardin-Favre, and more recently by Gauthier-Koyama-Vigny. And but the example to have here in mind, of course, is that if I take the family z square plus lambda, here this object is the boundary of the Mandelbrot set. I will try to explain anything in a way that it's general and can adapt it to any family, but I will always just talk about this family for simplicity. In particular, we don't want only to talk about dimension 1. I will talk about system in any dimension, and in particular, we'll consider endomorphism of the projective space in any dimension. These are a natural analogous of rational maps in any dimension. Notice that I ask that there is no indeterminacy set. It must be holomorphic on all the set. In this case, one can also define a Julia set as the support of a unique measure of maximal entropy. Don't ask me too much about the Fatou set because it's a bit complicated which Julia set I'm taking, but there is this. There is a Julia set, unique measure of maximal entropy. Let me mention at least for Sibony, and Duval or Sibony as people who really study in detail the property of this set. And if now I take a family, lambda, of endomorphism of pk now, so parameterized by holomorphic parameter, I can also partition instability bifurcation. This was a result that we obtained with Berthelot and Dupont, which is a generalization of this theorem in dimension 1. And in particular, what the crucial point here, that maybe here was a kind of second interpretation, although later very fruitful, but it was a later interpretation of the fact that it was a support of a measure, of a current. Here, the fact that the bifurcation is a support of a bifurcation current, again, measure if I'm in dimension 1, this is really central in all the approach. So the approach really relies on pluripotential theory. Now, the question that I want to address today, the general question, is can we study BIF in the sense of, every time I say this, I mean in a vague sense, can be the set, can be the bifurcation measure, can be any object related to bifurcation with dynamical tools. And of course, everything is dynamic, but I mean tools from the phase space, okay, typical of phase spaces. This is a general question. Now, while preparing this talk, I thought of a question that I thought was simple, but actually it's not. And so the question is the following, let me mention it. There exists a rational map such that the Julia set, say F, of F, is equal to the boundary of the Mandelbrot set. I thought that this had to be a question like quite naive or maybe folklore. I realize it's not. And so I don't ask you to think of this question if you get lost during the talk, which was my first plan actually. But instead I just say that this is no. The result is no. By result of Gioca and Krieger, Nguyen, in the polynomial case. So there is no polynomial, and Luo for rational map. So the answer is no. But the theorem I want to talk about today, at least in a vague form, which is obtained with Berthelot and Dean, is that, let's say in this way, if you allow me this slight unprecision to move between one parameter families family of the parameter space, I will say that every bifurcation locus, let's say for any dimension k or any degree d of the family, is the shadow, which I mean the image by a suitable projection, of a Julia set on a system of a higher dimension, higher than the sum of the dimension of the parameter plus k plus all the family. And this is true also that the bifurcation measure can be seen as a projection of a kind of a measure of maximal entropy on a suitable Julia set. So this, I say like this to say it's also on a measurable point of view. It's not a question only for the set. Is it a question? Yes. A projection, and I will define precisely which projection. Yes, I will build a set for which a reasonable Julia set as a definition, and the projection of this on the parameter space will be the bounded Mandelbrot set, for example. So, more precisely, going to construct a map I will call F from a space X to X, which will project on lambda, whose Julia set is something like here. If I take, for example, the parameter space, here I take the boundary of the Mandelbrot set. Here is my X. So this is my space X. There is the Julia set, which actually has a very vertical shape, and it projects exactly on the boundary of the Mandelbrot set. Really by the projection. Okay, again, I should state this theorem in the family, for example, of all endomorphism of a given degree. Yes. I will tell you which the space is in a moment. I mean, I will tell you which is the space and the map. Yes, yes, yes. But yes, it's proper because the fiber will be compact in any case. And to be like this. I have to define it. All the problem. It's all the problem. Yes, yes, yes. In lambda, yes, 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 it's a subset of the parameter space. Yes, this word for, I will only talk, as I said, of the family Z square plus lambda in this talk, but in a way that is adaptable to any space. So this in particular, I can do for another bifurcation locus of another family. But since I want to fix, I will work with the quadratic family to do everything explicitly. So, and why I want to do something explicit, I want especially to underline the fact that Berthelot and Dean actually already have this result, an approach that works for Mandelbrot, for precisely the Mandelbrot set. So for the Mandelbrot set is not new. For the boundary of the Mandelbrot set is their result. And the point is that their approach is very specific. I don't want to get to the point of Sebastian to say that there is a miracle for the Mandelbrot set, but I will tell precisely which are the point in the proof applied to the Mandelbrot set, which do not work in general. So which are really the tool new in this general case with respect to this one of the Mandelbrot set. So in particular, so new now, especially, but not only, the fact that the dimension is larger than 1. And so this will be the main point, not the only, but I will focus on this. So what is bifurcation? As I said here, there is a bifurcation current or measure. So in dimension 1, a tool which we have is that stability is equivalent, which is the characterization by DeMarco, to the fact that the Lyapunov function, let's say Lyapunov of lambda, is harmonic, pluriharmonic. Let me say harmonic for simplicity. I mean, DDC is 0, so DDC is equal to 0. What is this function? This is the function that sends lambda to the integral of log f prime of lambda in mu lambda. So this is the Lyapunov exponent of the system. And a possible equivalence is that for every critical point marked, but again, I just use one, Fn lambda, so the iterate of the all the critical points seen as map of the parameter space, if I iterate them with F lambda, this is normal. Okay, in dimension k, so stability is equivalent. As I said, we have a similar relation like this, so that L, so let's call this L, L of lambda satisfies DDCL is equal to 0, where now L is the integral of log of the Jacobian of f, which is the sum of the Lyapunov exponents in higher dimension. And what a possible replacement for this condition of normality is the following. This is equivalent to say that the volume of the image Fn of C, where F, we usually call F lambda Z, lambda F lambda of Z. So really the map of the family, okay? The dynamical system given all the family. The volume of the critical set, this is the critical set of this map, is a little o of d kn, and also, if you want a big O, of d k minus 1 n. These I have to really use the pk. So the idea is that actually this volume here is equal to the mass of the bifurcation, whatever we are using, times dkn, plus an error, which is not just a little o of this term, but is an explicit bound. There is an explicit gap between what I would have as a growth if there is the bifurcation, so dkn, or if there is no bifurcation, I jump immediately to the next one. Okay? So it's a way to detect bifurcation, just looking at the growth of the, for example, the graphs of the critical points. This maybe it's even an approach which is more similar to the height one, which was described before. I will really want to really make clear that then there is a gap between this speed and this speed, okay? And this is really the point. So a difference between bifurcation in dimension 1 and dimension k, because until now it may seem is the same story. Let me say a difference. Differences. The first one, which the more I think about it, the more I convince myself it's not the problem, but it's a symptom of a problem, is that in dimension 1, it comes from the same results I mentioned before. The stability locus is an open dense set. In higher dimension, there exist open sets in the bifurcation locus. So this is maybe the most striking difference. This theory can have inside the non-harmonicity locus of this function open sets. Now, what I would like to point out here as a difference is that in the Mandelbrot set, this function, the Lyapunov in practice, is the green function of the Mandelbrot set. So if one takes the bifurcation measure and the green current of the Mandelbrot set, they are the same. This is actually very special of the Mandelbrot set. Of course, it works in our other special families in dimension 1. But for example, since there are open sets of bifurcation, it cannot be true in higher dimension. So in general, let's say DDC, even if I work for measure of L, is not, let's say, the green measure, let's say lambda dimension 1, of the bifurcation. Okay? So we don't have this tool. We don't have that in general. Even if we have one-dimensional parameter, the bifurcation measure is not, in general, the green measure of the bifurcation set. Okay? And this is the main point. I really think this is one of the main points of difference. So, now, let me try to go in the direction to say what is a Julia set in a way that it will be useful. So here, so what I mean by Julia set? So Julia set. A possible way of all the possible equivalence approaches is to use the equidistribution of preimages. Dimension 1 or higher, by the results I already mentioned above. I do in dimension 1. If I take the sum for a given point y up to generic point, sufficiently generic, but I don't want to enter in this assumption here. If I take the preimages of a given sufficiently generic point and I divide by 1 over dn, in higher dimension I will put a k, this goes to the measure of maximal entropy. Okay? So this is a way, in particular, to define the Julia set, because it's a way to say, okay, what is the accumulation of these preimages here? Now, let's try, since we want to go and try to study bifurcation, to do an analogous of this, at least in the parameter phase space. So what we can do is that if I take here my parameter, and here I put P1 or Pk or whatever, a natural way, I use this dynamical system F there. So I have my parameter, and for each fiber, here I have lambda 0, I have f lambda 0. A possible way to construct an object which is similar to this is to take for every lambda a point and then to take them back all together. For example, I can take a graph, rho, and now I take all the preimages that, of course, they will vary with the parameter, but for every parameter, I will have a number of preimages. Okay? If I do this and I tend to the limit, I see that I get to an object. I will call it E, like this. And what does it mean that I tend to this? I can say, okay, answer dn, the sum of the integration on the graph of, let's say, rho j tends to an object where for every row, let's say that I call n j. So rho n j it's a numbering, it's a number of the n preimages of this graph. So I have a graph, I take the d power n preimages as graph, and I take their integration in the same way that here this was the integration on a point. So this is an average of curves now in my space, okay, of the actually surface of the dimension of lambda. It goes to some set. What I know of this object. But for every slice like this, actually I'm doing nothing else than taking a point and taking the preimages. So this is an object. It's a form, if you want. It's a singular form, but with the property that every slice is the measure of maximal entropy of the corresponding parameter. Okay? So I'm just putting this theorem here in a uniform way. This goes to this one. So this is an object such that E restricted, if you want, at lambda is the measure of maximal entropy. This is for one who would like to ask more precisely, the 1-1 positive closed horizontal current, but it should be enough to say that it's a form whose lies, singular form, whose lies is the measure of maximal entropy. Now, we want to get to bifurcation. So what is bifurcation? It's not only this, because this construction does not distinguish any parameter until now. All parameters are the same. We cannot see bifurcation in this picture. But what is bifurcation? So if I want to take the DDC of L, I will do something that I will never want a student to do, but I have to take DDC of the integral of log f prime mu lambda. Let's say that I can do DDC of log f prime against mu lambda. Now this is the integration on the critical set. Now, this, I mean, now I'm working in a product space. So what's happening here is that in practice, if I take a critical set, oh, it's not this. If I take my critical set here, the bifurcation is, so the bifurcation, tbif, this is equal, so to the projection p lambda star of the object, which is E, intersected C. If this was a form, you should think of this just as the restriction of this form to a critical set, okay? Think of it as a graph in dimension 1. You have this, you restrict this bit singular form to this object here, okay? This you project, all the intersection you get. This is the bifurcation, okay? So, this is the, in practice, rewriting this formula. So a theorem which is not obvious, but true. Theorem, let's say not obvious. It's I mean, I use it several times, but it's kind of implicit in the work of FAM. It's not stated in this way, but it's kind of implicit in the work of FAM. So I'm citing as his theorem. Is the following. If I take, I may ask, okay, I have this convergence. This goes to this. Can I take wedge C and wedge C in practice? If the intersection with C was smooth, of course it would be true. I'm just multiplying by a smooth form. C is singular. So a priori it's not clear why this convergent should pass to the convergent that I'm writing now. Let's call all these objects for simplicity maybe Rn. From in practice gave the argument that proved that this goes to E wedge C. This actually I can take all those or the current constructed in this way, like an average of graphs, or actually it's true for every smooth sequence. If I here take a sufficiently good chosen sequence that smooth that converges to this one, then I can wedge with the critical set, which means I can restrict the problem to the critical set. Why I'm saying it's not obvious? Because usually in order to get an intersection with a singular object, you need a good control on the speed of this convergence. And this is in practice the result by Pham or Odin-Sibony, that if you can get this convergence very explicit, exponentially faster with explicit bound, this will pass with intersection with this singular one. Okay, now the problem. I said I wanted to interpret the bifurcation now in a dynamical way. For now, I didn't do anything dynamical because I wrote the bifurcation as, which is if you can project and project, as a limit of things, but it's not the action of a dynamical system. I'm just acting, then intersecting, and then projecting. It's not a priori only dynamical system acting. So, problem, how to make this convergence a dynamical one. So what I want to do, so is to take a space, define a map, F, and I would like something like this. For some forms of the good degree that I will define, I want to take the pullback of these forms, Fn star, by this object on X, okay? I will normalize by something, that will be the average growth of the mass, whatever. And this will tend to a current S on X. But the point is that this set here will project on lambda. And for example, S, a suitable projection of S will be the bifurcation, the BIF. What do I mean is that in this space X, I have the picture I have there. So not only I have something which projects on the bifurcation, but I have an object set for every form, sufficiently generic form of the good degree. The limit, so lambda, and he did this X, the limit, I take something, a form, it converges, and at the limit is a vertical object that I will describe a bit better, that projects precisely on the bifurcation. Okay? So this is how I will reconstruct the bifurcation. Okay? As a big dynamical space, a big convergence in the spirit of this one. It will not be point, it will be form of a good degree that we now will see. But in this big space, if looking from like this, we will see the Mandelbrot set, okay? Or any other bifurcation that we want to consider. Okay, so how to do this? So let me now define the space and the map. So I say that f of lambda z is a notation for lambda f lambda z. Now, let me define, so a first space x, which is lambda times, let's say, ck, and then I compactify. So if this I was taking a c, I'm just saying, okay, my space is the parameter space, which is c. Here I have ck or pk, and then I compactify as a p k plus 1. I consider together parameter and z, okay? This is already the point. Z, x, the first space is all together. Now I take this. In this space, I can consider at every point the Grassmannian, which is given by the k plane in this k plus 1 space. Don't worry, in a moment, this I will take 1. This I will take 1 because I said I will study the Mandelbrot set. So actually, this is a P2. The Grassmannian is dimension 1. is just lines around the point. Yes. Lambda? Lambda is C. C. Which is C? No. Yes. Actually, yes, I can do this for the family of endomorphism of PK of every degree, but I do it by slicing on lines, quite generically, but it's always line. Yes. So yes, it's a line. It's yes. Actually, you want lines which intersect the bifurcation in a compact set. This will come later, but it's they're quite generic. So the point here, I have FP2. This dynamical system, I sit on P2. But now I see together the variable lambda and z, okay? In particular, I have vectors. And so I take as a vertical a P1, which is the parameter for every point. I have the parameterization of the possible direction at this point, okay? Now, what's the map? My map F of lambda, z, and say a vector v is lambda, f lambda of z. And then I take the differential of f at the point lambda z of the vector v. So I'm seeing how this map here moves tangent vector, okay? In this, which is all my family space, okay? This is all my family. A vector which does not have to be in a phase space, can be actually generically is transversal, will move with a differential. Okay. All now the goal is to say that this object can detect what the critical set does, because this is all the goal. So let me now, so the picture here is to say, okay, maybe I put it larger. I have my space X. This is lambda, let's say dimension 1. This is C, if I'm doing the Mandelbrot set. Now I take a generic line L in my space here, P2. And here I take my fiber, which is P1 also. Okay? And now I lift this line. Lift means it's again a line, but for every point, I lift with a tangent vector. Okay? Is a line, is a two current. Two current. So line, two current. This, the space of these lines, or the form which was smoothing of these lines, or in any case, this cohomology space, is this degree that I want to use here. So I want to now use the lift of generic lines here, but seen in the tangent space, as something that can recover the bifurcation. Okay? Now I have this. I have L, and I have the hat here. Notice that this is a, in this case, this is a line, and this is also a line, because I just lift with one direction. Of course, in higher dimension, we will have a Grassmannian to take care, but we are not doing this now. So, claim. The claim that I'm making. Claim. Now, if I take, let's say, Ln, which is f minus n of L, so this line, which I can see as a graph on lambda, is of the type we were studying before. So I take the preimages. It's, I don't know, it's something. Actually, something like this. This is Ln. I take Fn. It's something of this picture here. But then I lift. Now, I want to see it here. I have this. I take Ln hat, which is actually the pullback of L hat by this system. This can be seen that it's commutes. And I take this, and the claim is that if I divide by n the n, notice the n, this goes to a vertical current in X. I didn't say, but this is X. This is X. This is my space, which projects on the space of my family, which projects on the parameter space. So this is this goes to a vertical current on X. And now, let me say that I will not describe why this becomes vertical, okay? But I want to say, okay, how now we describe the limit. But notice now that I can take any, for example, the infinity here. I take the copy of X, which is here, this X here, a copy of my family. And in order to understand what does a vertical current, I have some measure here now, and it's just vertical. So to understand the limit, it's enough to understand the trace here on every horizontal plane now, okay? I'm not taking this because otherwise I didn't need this to do the problem. So now the question, so the claim is that this here is the trace on, let's call it V, maybe here, this one, I'll call it V, big V, is for every lambda z, I take the vertical direction, okay? The point which is infinity here, the vertical direction, the direction parallel to z, to the plane z. I take this system. Now, if it's a vertical current, wherever I slice, I always say the same object, okay? My claim is that the trace of this is the integral against the bifurcation measure, and dimension 1, of all the maximal entropies. If you think of this, even if I don't lift here, if you want to say what is, for a family F, the analogous of a measure of maximal entropy, should be something related to the bifurcation, because it's the most chaotic in some sense in the parameter direction. And then in the vertical direction should be all the measure of maximal entropy. This is the natural candidate to say is the maximal chaos object in a family. Okay, is not only this with all the bifurcations, all the maximal entropy measures, but them only on the bifurcation point and parameterized with a measure which is the bifurcation measure. So this is the good object. I define it by, I don't know, mu, like this. So the point here is if I get to vertical, y, the trace on v or on x, whatever, is precisely this bifurcation, because this will give a meaning to say, if this is true, I can recover in particular the bifurcation or whatever problem down now, the bifurcation here, for example. I have my current S, I project down here, and I project again on lambda, and I get the bifurcation, the locus or current or whatever, okay? So this, in my mind, is recovering the bifurcation from a dynamical point of view. Because this is a current, which is, let's say, some kind of projection of mu. And I pull it back. P from maybe this one. Okay. In order to do this, I want to explain, I will not give all the details, but I want at least to explain two things. One, why there is the n, and why we should expect the n. And second, actually, at least what is the relation between these objects and these preimages with a critical set, because we will need a critical set at some point to get to this object. What's the relation between this and the critical set? So let's try. So the question is, what is Ln hat intersected with V? So I'm taking the pullback, okay? I have a lift, I take the pullback. Now, sometimes, I mean, often they intersect this. And I put all the dimension in place so that these are points. Because this is a line, I intersect with these two planes, I have points, okay? V is the copy of my family space here with the infinity here. The vertical is a P1. I take the point which is the vertical direction, which is parallel to the dynamical phase. This I take infinity, so I take the vertical tangent for all the points. It's a copy. And I'm using this now, and you will see in a moment why. So what is this intersection? What does it mean that here in my picture, I have V, and Ln intersect this? What does it mean that I have an intersection? It means that this, recall that the image of this is L hat, is some line. It means it's a pre-image of L hat, of L, which at this parameter has tangent which become vertical, which means it intersected the critical set in order to become vertical the tangent. So if there is this, an intersection between a pre-image lifted and V, there exists a critical set, a critical point for Fn. Notice the iterate here on this one, on the space X. Because I have this one, I have an intersection. In the space here, it means this vertical direction, the curve is done something like this with a vertical with a vertical tangent. Okay? Because this vertical tangent in this one. This is the pre-image of a line. This means I cross the critical set to get the vertical tangent. Now, what is the critical set of Fn? Is the critical union the f minus 1 of the critical, blah, 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 f minus n minus 1 of C of the critical. These are n terms. okay? There are n terms because I have n choices to get this picture. My Fn, I can have intersected in n iterate, one, twice, the third, the fourth, and I have n choices to intersect the critical set. So each of them, so I say n terms, suppose that now I'm saying, okay, I'm trying to do, so for each of them, what do I know? I know the non-obvious fact that if I take ln and I divide by dn and I wedge with C in my space here, the family, and I project, this is the bifurcation. This one. Because the bifurcation, I can detect it taking pre-images of generic graphs or smooth objects and intersected with the critical set. This, by the non-obvious fact of FAM, goes to the bifurcation. Okay, I'm just saying here how to recover this. Then one needs other argument to say, okay, in the vertical, I actually have the maximal entropy, but this is easier. This is a way, at least to give the idea of why, in this extended system with the tangent, seeing if I have this maximal growth of the tangent, because now I say, okay, if I want n, in order to get the growth n times dn, I need to have passed by the critical set. Okay, I need to have passed by this. And if I do, I have n choices to do. I have all the n pre-images. And each of them will give me a contribution, which is mass, which gives me precisely the bifurcation. So this tells me that n over dn, but it gives me this actually. It gives me this, that if I take this, I divide by dn and n, I go to a vertical current. I only prove this part. I still don't know what are the vertical conditional measures, but I will not prove this now because it's just the fact that there is the equidistribution of pre-images on every fiber. So this is easier. But the real point of the n is the one that gives this one, okay? And come from this idea of intersection in the lifted space. Now, at this point, you may tell me there is a problem. You are very nice not to tell me, but there is. And is the following. We did what we did. We did the limit over n of ln hat intersected with v. Okay, we did this, right? For every n, I counted all the intersection, and they said it's related to the bifurcation. But this, what we really wanted to do, was the limit of the ln hat intersected with v. First, I do the object, and then I should find the trace. We did this. But actually, this is what we want. A priori. Is another problem of intersection of currents with a very singular object, which is the vertical one. This, there is no way to do a smoothing because we are used in a crucial way that is really the vertical one to have the interpretation with the critical. There is no way to solve this by smoothing a bit v because it loses all the construction we had with the critical set. So this is a problem. And this is a problem that, for the reason I'm going to say in a second, is not there for the Mandelbrot set. Why? Let's maybe say, since it's a conference of dynamics, why this is a problem, because this is actually a quite delicate point of potential theory and intersection of currents. So I will maybe spend a minute to say why this is a problem and why this is not always true. Just to know which is our enemy, what we have to fight. Suppose that I take maybe V. I have this picture, very simple. I have V, and I take the graph yn, which is yn is equal to x. Maybe I did the wrong coordinate, but it should be something like this. Okay? If I do n going to infinity, what happens? But if I do V intersected yn, this is delta 0 for every n. For every n, this becomes more and more flat like this, but for every n, it's delta 0. There is nothing, okay? But if I do the limit of yn, and then I intersect with v, First I do the limit, so it becomes actually very flat. Actually, it's S1 times the integration on this. It is one on the boundary. So this is a copy of, let's say, Lebesgue on S1. So if I first take the limit, this becomes more and more horizontal, vertical like this. And in the limit, I just have the measure, which is here on the circle. This is a general problem. It's not true in general that these things are equal. And this is really, in practice, the problem that there is intersecting currents. So now, on the other hand, it's not all lost. We know that delta 0 is less, I use this notation of Lebesgue on S1. And by this notation, I mean when tested again all subharmonic functions. This is true, because by the definition of subharmonic function, the value in the center is less than the value on S1. This means that for every phi subharmonic, phi delta 0 is less than phi Lebesgue on S1. Okay? So at least I have this. What is this? So first I have to put the limit. So this is like this. This I have it. Yes? Yes? Question? So I have this. Now, if I'm working with the Mandelbrot set, so we found this one, but we have for free that the equilibrium measure of the Mandelbrot set maximizes the integral against subharmonic functions. So if you are working with the Mandelbrot set and with the green measure in general, this is for free. Because the object that we want, which is the green measure of the Mandelbrot set, always satisfies this because it maximizes this relation. So for Mandelbrot set, as soon as you get here, this is fun because this one is free. Whatever you get, it will be maximized by the green measure. This is not true in general, even for families in dimension 1 in general. If you have more than one critical point bifurcating, it's true. Maybe, yeah, if you have one critical point, it's fine, but with more critical point, it's not true. Higher dimension, no way. So the point is how to get this one. This is the main point, actually, the main problem, actually. What I discussed here is, it's important, but the main problem is how to get this one. And I hope I convinced you that it's not true in general. So as often in dynamical system, we want to prove something which is not true in general with some assumption coming from dynamics. Otherwise, we will just prove some general convergence. And so there is not a general criterion to do this. 5 minutes, 1 minute, 2 minutes. Okay. Okay. The idea is the following. How to solve this? You want to exclude that in some sense your Ln that go to intersect V have a lot of tangency with V. This is the problem. And more tangent as n go to infinity. This is the problem. 5. There are questions. I can. So we want to exclude that there are many tangencies between Ln hat and V. Because if we can prove that suppose we can prove that there are never tangencies, okay? It means that the picture that I just erased is not there. It's always well transversal. So this will be the good. There is V. The good case is this. It's like this. The bad case, good. The bad case will be that you have a lot of intersection like this. And actually not just that there are. They become more and more flat as n go to infinity. So this is the bad thing to exclude. We don't want this. Okay? To V. This is V. This is V. Yes, I put this, but it's in this case it was horizontal. But it just means that my Ln should not be arbitrary tangent in this way. Otherwise, I cannot pass to the limit in that one. If they are arbitrary tangent, I have the problem of the delta 0, and so I will lose the limit. So I want to prove that there is, for example, some bound or whatever. There cannot be too much tangent to this surface there. Yes, I'm getting there. I'm getting there. Dynamically, we have an extra information. We have already the information that we don't know how, but we know that our object, I said, becomes a vertical current. If I put in this coordinate, our limit is something like this. This is the limit, as I called S before. So we have the dynamical information that in the limit, it goes to an horizontal object, which is horizontal in the sense really pulled back by a projection of really a measure like this. So we want to use this information to say, my sequence of currents cannot become too flat, otherwise we will not be able to do this picture. I don't know. I will give a way to say this, at least the idea. It's, I don't know how many of you didn't like when I lifted the system, because I have to lift again. I have to lift a second time. And the idea is this, geometrically, what does it mean, this tangency? That if I lift a second time to another tangent, now I have an intersection. So this means if I lift now an extra time to x hat, so again, don't let me write you what it means. It's another tangent, another Grassmannian here, and another action of all the differential of the first part. If I lift here, this a tangency become again an intersection upstairs. If it's not tangent, just an intersection, when I lift, they become different points. Okay? So this is really the point. This is the bad problem. We want to say that in this further space, here I have no intersections once I lift again. So in this lift space, let's say that I have V and I lift it once. I take a tube around V. And now I also take my double lifted, let's say Ln hat. Don't ask me too much how I'm lifting, because now it's a bit imprecise. I should now start lifting in a different way, but suppose that I can lift another time. It's an object, okay? These are the second lift of a L hat. I want to say that they don't put too much mass in this neighborhood here. Because if there is no mass here, it means, but intersection means tangency. Being close to intersection means almost tangency, which is equally a problem. So I really want to say, no, everything is well disjoint. But what's the point here? I know that this object here goes to S, which is of the form P star of some measure that we said before. And it's for the picture, they are transversal. V is like this, and S is like this, is the blue one. So S and V are transversal. So since they are transversal, the mass of the lift of this in the neighborhood of this is 0 when I lift here, S hat, as mass 0. So in the limit, these objects will put mass 0 in this neighborhood of V. And this will tell me that, okay, asymptotically I have no problems of intersection here, which I can push down, and I say, okay, it's really the slice that I wanted in the limit. For people closer to this topic of intersection of currents could recognize behind here the theory of density of the Insiboni. But this is really just a small part of this theory, because there is a lot of dynamical information and less of general theory to be used, because it's not so needed all the theory to do this. Okay, so I think I can stop here. Thank you very much. Thank you.
Do we have any questions?
Thank you. How constructive is this? Is this something that I could like 3D print if we found the function or something?
No. Already for Mandelbrot, you need the C3.
C3, but then can you just find a three-dimensional sub-projection that the projection works out?
No, I mean, which object you would like to have explicit of this C3? No. It's
like the Julia set in C3, and then you find a three-dimensional projection of that, and then you have that to print. Does that sound possible at all?
So the answer is there.
Okay.
Because no. I mean, what you are asking is it true that the construction I wrote works well when slicing by some plane? It's not always true. This is a very precise plane for which the construction can be sliced. In general, the problem of saying I have a big object and I slice and I see the good image is not so well defined in this kind of problem. So in this case, if you take a slice, maybe generic, maybe well chosen in this way, yes. But in general, no.
Okay, thank you.
Any other questions? Yes.
So if I understand right, capital F is not, okay, there are several capital F. On X is not regular in general, right?
No. Studying the indeterminacy of this is an important point. Yes, it's studying. Basically, everything I said, we have this intersection, we count them. We have to say, one, they're all transversal. Second, you don't lose too much at infinity. Third, there is not too much indeterminacy set which you lose pre-images. Yes, is a very important point.
Okay, so your main theorem is that under certain conditions, then you have what you claim that bifurcation locus is a projection or something?
I'm saying that on the family of endomorphism of pk of a given degree, yes, I have this theorem because I can reconstruct the bifurcation by slicing for a generic line. And for a generic line, I have this theorem, yes. I don't have for all lines.
Any other question? If not, let's speak. Oh, okay, so let's thank the speaker again. Okay, welcome back. So the second talk this afternoon is going to be given by Leticia Simon Pardo. Or Pardo-Simon, sorry, from University of Barcelona. So and she will speak about grand orbit relations in wandering domains.
Thank you, Luca, for the introduction, and thanks to the organizers for bringing us here together and giving me the chance to talk about their work, our work. So today I'm going to talk about ground orbit relations in wandering domains, and this is based on joint work with Vasily Dorido, Nuria Fajeja, and Lucas Geller. So today, in this talk, we're going to be iterating rational or entire maps. So we have our space S, which might be either the Riemann sphere or the complex plane. So what are ground orbits? So you have one point in this space, then we define its ground orbit as the set of all points that some iterate coincide with some other iterate of my original point. So perhaps it's better if we look at this picture. So we have our point set, we have all the forward iterates, also all the backward branches, and also any other branches that, of points that eventually map to some iterative set. Okay, and we might also talk about the ground orbit of a set of my original space, and this comprises all ground orbits of the points of the set. So the union of all these ground orbits. Now this defines an equivalence. Ground orbits define an equivalence relation in the ground orbit of my set. So if I have my set V, then 2 points are going to be in the same equivalence class if they are in the same ground orbit. And now I'm going to say that this ground orbit relation is discrete for the ground orbit of my set V or U, which we call V, if the ground orbit of all points of each of these points is a discrete set for my space. And otherwise, as long as there's one orbit that is not a discrete set, then we call it the relation, we call it indiscrete. So now just to set some notation, f of f is going to be the Fatu set. So if you're not very used to iterating entire maps or transcendental maps, this is defined as usual in terms of normality. And the Julia set is the complement, the locus of chaos. Now, Fatu component is just a connected component of the Fatu set. And the goal of this talk is to understand ground orbit relations within Fatu components or in Fatu components. Now, if we have a periodic Fatu component, in most cases, whether this ground orbit relation is discrete or indiscrete is an exercise that we can try to do together now. So suppose we have an attracting basin, which is not super attracting. So we have, and just for simplicity, let's suppose we have a fixed point. Oops, sorry. Yeah, I don't know if you see the pointer. Yeah, we have a fixed point at 0. And well, so let's take any other point in this basin of attraction in the same component, let's say. And then we want to understand how this ground orbit of this point looks. So we can do the following. We can start iterating. And now we know that in attracting basins, we have to have at least one critical point. We have one critical point, which means that there's some degree. So if I take any point, chances are that as I iterate, and now I look at the preimages of this point, well, I have more than one. And I can keep doing this process. I keep iterating, and then I look at the preimages of those iterates. And what happens is that At some point, as we know, in a neighborhood, locally, we have linearizing coordinates, which means like basically I'm like a lambda set, which means that I am one-to-one. So as I keep iterating, at some point I will land in some region so that when I go forward and then I go backwards once, I won't multiply the number of preimages I have. So what does this mean? This means that I won't be increasing this number as I go forward. Of course, as I go backwards, I will have preimages of my original points and all the others, but this will accumulate towards the boundary. And I can conclude that this set we could prove formally that this gives us that this is a discrete set in my basin of attraction. So this means that the grand orbit, as we defined it, is discrete. And now I removed my fixed point, the grand orbit of the fixed point. In this case, it's also discrete, but now we'll see that this is kind of a special point. Okay, and here I marked some domain in gray, and this means one could see once we take these linearizing coordinates that actually you have a region. So if you quotient your domain by this equivalence relation, you would see that you have or before you quotient, you can have this kind of annuli where each point has one representative of the grand orbit, and actually this line is identified with this. So if we look at the surface we get as we quotient our attracting basin by this equivalence relation is a torus. Now we can perform a very similar analysis if we have a parabolic basin. Now this time the fixed point, let's assume it's a fixed point in the boundary. And again, we can play this game. Oops, we can play this game of iterating forward and then backwards and counting how many preimages I get. And again, we will land in some region where I start being one-to-one. And therefore, as I go forward and backwards, I'm not multiplying the number of preimages. And again, I can conclude that the grand orbit relation is discrete. Now let's move to superattracting basins. So I have a superattracting fixed point. We can think of this. I know my pictures are not I didn't worry where these preimages are. I was just counting. So let's suppose we have a fixed point, and this time the derivative is 0. Let's think it's set to the d, or set square if you want. And let's take any other point in the superattracting invariant basin. So as I go forward, we know it's, let's say it's set square, and I go backwards, then now I have 2 preimages of that of f of z. As I go f square of z, and I go backwards, I have 4, and so on. And moreover, all these preimages are in a circle of the radius of the modulus of my original point. And this time, as I keep going forward towards the superattracting point, I don't have any region of injectivity. So I keep going forward and backwards. I keep multiplying the preimages. And in fact, we can see that they are dense in the circle of radius, the modulus of my point. And in fact, the grand orbit also, well, all images will also, as I go forward and backwards with all these points, they will accumulate also in the image and so on. So this time, I don't have a discrete set. I will actually have an indiscrete set. So now the grand orbit in my component has relation is indiscrete for any point is a discrete set, except for my fixed point, right? So I remove that. And if we have a rotation domain, let's say we have a single disk, as I keep, so we have a irrational angle, and as I keep iterating, I go around these curves and my images accumulate there. So again, I get an indiscrete relation other than for the fixed point, which has a discrete orbit. Okay, so if we are iterating rational maps, then we are done with periodic components. We have classified them. The grand orbit relation is discrete in grand orbits of attracting and parabolic basins, and it's indiscrete in rotation domains and superattracting basins, as long as I exclude orbits of periodic points. However, if I'm iterating a transcendental entire map, I'm not done. There are 2 possible extra types of Fatu components. We might have Baker domains, which are periodic components where my points converge towards the essential singularity at infinity. Or we might have wandering domains, which are the Fatu components that are not periodic nor pre-periodic, or equivalently, Fatu components such that no two iterates ever intersect, are pairwise disjoint. So, okay, so let's continue our analysis. If we have Baker domains, this time is not an exercise all of us could do here, but instead it follows from work of Cohen that the orbit relation is discrete in a Baker domain. And if you've thought or studied Baker domains before, you also might know that you have this kind of absorbing domains where you are eventually also one-to-one. So you can imagine you could also argue like this. And well, Fagege and Henriksen studied in more depth grand orbit relations in Baker domains. And in fact, they classified them into 3 types. So if I have a Baker domain, let's say it's like this, I can take Riemann maps, I can move it to disk, and I can study them in the disk, and we can think of one as the point at infinity. And it turns out that there are 3 types of, the resulting map can be classified into 3 types, which they call hyperbolic, doubly parabolic, and simply parabolic. So now if we are interested in looking at how it looks, the set where I have my Baker domain modulo the equivalence relation of the grand orbits, then it turns out that in the hyperbolic case, hyperbolic means like basically in this domain, I'm converging like if I had an attracting point, and then we have at the surface is like a cylinder, finite cylinder. In the simply parabolic case, we would have that it's a cylinder that only goes infinite in one direction, or the double parabolic one, an infinite cylinder. Okay, so now what about wandering domains? So now we say, okay, this is always discrete in all cases. And let's look at some examples of wandering domains. These examples were provided by Fagege and Henriksen when looking at grand orbit relations. So here we have the map z plus sine of z plus 2 pi. So all these regions that are here labeled as W0, W1, W-1 are wandering domains, and they have a critical point that maps C-1 to C0, to C1, to C2, and so on, and also backwards. And so these are wandering domains that march towards infinity, towards the right. Then here we see preimages of these wandering domains, and in white you would see like these hairs in the Julia set that we know also happen for transcendental maps. So all these gray sets are in one grand orbit of wandering domains. And now let's try to figure out what the orbit relation is. Well, to do so, it would help us to have this piece of information, which is that this map is actually the lift under the exponential map of our superattracting basin. So a tool or a way of generating maps with wandering domains is if we have a self map of the complex plane -0 with some periodic Fatu component, let's say fixed, then we can take the exponential map on both sides, and this will have infinitely many preimages. It's 2 pi periodic. And it might be that this time, here I was fixed, but now I'm mapping my map upstairs, map one preimage to another one, and this generates an orbit of wandering domain. Well, it turns out that this map can be obtained as the lift as this other map which had a superattracting basin. So now we can say, oh, we know superattracting basins have indiscrete orbit relations, so perhaps the wandering domain also has it. But now we need to be a bit careful, because before, when I was looking at when I was doing this game of going forward and backwards, I was stacking all the layers of preimages one on top of each other, but now I have a wandering domain, so they're spreading in the orbit. So I can play, good news, I can play a similar game, but I need to be slightly more careful. And in this case, because we have a critical point mapping to a critical point mapping into a critical point, we have some sort of these equipotential curves. So I try to draw them. So if we take, won't be exactly like this, right? 1 point, and then I go forward. Well, I have some degree, right? In this case, the critical points are of degree 3. So when I look backwards, I have 3 preimages, and because of how my wandering domains are so symmetric, I still have that preimages as I keep going forwards and backwards will also accumulate in some sort of curve. And I can also conclude that in this case, the orbit relation is indiscrete. So this is our first example for wandering domains. And now let's look at another example, again, provided by Fajej and Henriksen. So now we have this other map, A plus 2z minus e to the z for some constant, A precise constant, but we don't care here. What we care about is that there are these, this map has these domains in gray that we want to study. D minus 1 is tiny, sorry, D0, D1, and perhaps you can recognize some shapes. Well, it turns out that these wandering domains are again obtained as a lift of a Siegel disk this time of this specific map here. Okay, so we again know the orbit relation in Siegel disk, which is indiscrete. And now let's try to use this information to get the orbit relation in the wandering domains. Well, this time, what happens is that when I was looking at the orbit relation in my Siegel disk, as I was iterating forward, all images are in the Siegel disk, right? But now, if they're in the wandering domain, I can think of like, I have a lot of sheets stacked on one on top of each other, and now I spread them. So what happens is that in the wandering domain, as I keep iterating, I just have one image of the point F1, F2, F3. They belong to different wandering domains. So in fact, when I do this lift, now my wandering domains, my map F restricted to the wandering domain is 1-to-1. So it's no longer indiscrete. Now we have an example of a wandering domain where the ground orbit relation is discrete. And I put 2 exclamation marks. One to say like by lifting, we move from indiscrete to discrete. And also the other asterisk, well, we have 2 examples and one had discrete and the other one indiscrete. So let's summarize it. We have transcendental entire map given a type of periodic Fatu component. We know that if it's attracting is discrete, if it's super attracting is indiscrete. For periodics, Baker domains always discrete. But we've seen that there exist examples where the orbit relation is discrete and where it is indiscrete. So now we can update our goal. Perhaps we're happy enough. We say we kind of understand ground orbit relations in periodic Fatu components. So my goal or our goal can now be to try to understand it in wandering domains. And you'll say, okay, but why? And also, this conference was, yeah. Can I answer your question in 5 minutes? Okay, good. But why we care? Well, maybe you like this question, and that's or you think it's fun, and that's a reason perhaps good enough. But also the motivation behind for us is that this is related to the formation spaces, and I want to do a parenthesis in the next 2 slides and talk a little bit about the motivation. I know I will be too vague, perhaps for people who don't know about this, and maybe too imprecise for those who do, but sorry, let me just try to motivate a bit why we're looking at this. So if we have a holomorphic map, we might want to understand the other maps that are conjugate to my original map F, and perhaps we want to ask for some degree of regularity on this conjugacy. So maybe we want to understand the space of holomorphic maps that are quasi-conformally conjugate to my original one. So I have the same dynamics and I have some deformed picture by a quasi-conformal map. So, okay, so I can look at the set of holomorphic maps, and this is equivalent to looking, well, have this phi quasi-conformal, so it's the set of quasi-conformal maps for which F, the Beltrami coefficient is F invariant. Okay. But now, if we want to understand this set, we might want to consider the deformations under these files for files that are essentially different. And what do I mean by this? Like, I will want to quotient by something. For example, if I can obtain two of these quasi-conformal maps via conformal isomorphism, well, that's basically the same deformation. So I want to count it as one deformation. And I will want to do other identifications as well. And okay, so I have this set, I do these operations, and now I also want to have a space with a nice notion of dimension and perhaps a complex manifold and so on. So I might want to study the Teichmuller space of my function. So, okay, so if I want to do this, just let me give you a little bit of notation. So let's denote by S of f the set of singular values of the function. So these are the critical values and the asymptotic values in the case of transcendental maps, and pair of f the set of periodic points. And now we define as S hat and J hat the closure of the ground orbits of these respective sets. Well, if we do this, let me point out that we're taking ground orbits. So yes, these sets are completely invariant, and the Julia set is contained in J hat of F. Now, a little bit more of notation. So let me define as F hat of F of the Fatu set minus this J hat. And, well, okay, this is a set that has the Fatu components where I've removed periodic points, ground orbit of periodic points, as we already did, but I also want to remove the ground orbits of the singular values. And, well, this is a set which I can partition into two, depending on whether the ground orbits are discrete or are indiscrete. So, we've all done all these because it turns out that Sullivan and McMullen proved for rational maths, but also they developed a general framework to study the Teichmuller space of these maps. Here I would have to have a hat if I'm rational. And it turns out that I can study these deformations or study this space by studying separately the Teichmuller space restricted to J hat, and this is related to existence of invariant line fields and so on, something we won't get into today. Times the Teichmuller space is restricted to when the subset of the Fatu set where the orbit relation is discrete, times when it is indiscrete. And this was then extended to entire maps by Fajay and Henriksen by dealing with the presence of asymptotic values. So now, if we want to try to apply this theory, if we want to look at the formation of maps with wandering domains, we need to understand where they fall, right? So, so that was our motivation behind. And all we knew to that point when we started looking at this a couple of years ago, where what happens for period of Fatu components, and these examples, a few more of wandering domains. So before we move to the results on wandering domains, let's revisit for a minute the analysis we did on periodic Fatu components. Well, I removed the periodic points already, but I would have to, if I'm looking at this component, remove the ground orbit of singular values again. And note that if I'm in a attracting or parabolic basin, then F hat intersection U is at most one connected component because these ground orbits of my singular values will be discrete. And if it's super attracting or a rotation domain, and then I have some singular points, some image of some critical point landing there, this analysis we did that their ground orbits are indiscrete applies to the singular values, and then I will break my Fatu component into several of them. But note that the analysis we did applies to each of them. So each of them will have either indiscrete or discrete as we described. And note also that if we are a Fatu component of an entire map, even if we are an attracting basin, now the component might break into several components because we know we can a priori have even curves or asymptotic values and so on. Okay, so this set, we are interested in understanding the ground orbit relation of wandering domains. And we realized, well, as we all know, we've learned over the last few years, from Phil, Gwyneth, Nuria, Anna, Vaso, Gustavo, that wandering domains might have different internal dynamics. This big casuistics. So our question initially was like, okay, is this related whether we have in discrete or discrete to these internal dynamics? And also, when we were trying to look for examples, we were also wondering about this definition of when it's discrete or indiscrete or different characterizations that helped us. So that led us to ask some rather seemingly basic questions about the problem. So for example, can points with discrete and indiscrete grand orbits coexist in a single component of f hat? Because remember, when I defined in the first slide what was if the grand orbit was a relation was discrete or indiscrete, I said, as long as there's one point for which the grand orbit is indiscrete, I call it indiscrete. So then we wonder, can they coexist in a wandering domain? These points, I would say that the orbit relation is indiscrete, but could I have points with discrete? Now I don't have periodic points, of course. And we know that this cannot happen for pre-periodic Fatu components. And well, it turns out that it cannot happen for wandering domains either, but it had to be proven. And we gave a few characterizations to check our criteria for discreteness. So our first theorem says that if we have a wandering domain, and we have V is the grand orbit of this component of this grand wandering domain. Now we say it can break into several. So it's equivalent to say that the grand orbit relation is discrete. And Vukash, it's equivalent to just checking it for one point, because then it will have to be for all of them. And talking about wandering domains, this proof applies to any Fatu component. But we also gave a couple more of criteria. So also if there is a point, for each point, there exists a neighborhood for which for each point, I only have one representative of the grand orbit of the points. And also, if you remember, when we did our analysis in periodic components, we related to whether the map eventually entered a region where I was injective. And in fact, this is also a criteria. So if there exists a simply connected domain or where my function, all iterates are one-to-one, are injective. So this is our first result. And another question you might ask is, can components of f hat with discrete and indiscrete grand orbit relations coexist in a single wandering domain? So we've said it breaks, it might break because of the presence of the grand orbit of singular values, the Fatu component, and we've said that it cannot happen in periodic Fatu components, but it turns out that this is possible for wandering domains. So our second theorem says that there exists an entire function with a simply connected wandering domain, such that the wandering domain, once I remove this grand orbit of singular values, breaks into two components, and one of them has discrete grand orbit relation and the other one has indiscrete, which perhaps rather strikingly, if I can say. Now, let me point out this theorem says simply connected because it turns out that for entire maps, we might have wandering domains with holes, we might have multiply connected wandering domains, but if I'm in a multiply connected wandering domain, the grand orbit is always indiscrete. Why is this? Well, it follows from the thorough study of Ripon, Stala, and Bechbeiler that we understand pretty well how these multiply connected wandering domains map. So we have some, let's say, sequence of annuli, one surrounding the next. We keep iterating, and we also know that these annuli get thicker and they have big rings where my map is like a power map. And from there, one could do, probably they already knew if they were interested, that you can do a game similar to when we had a super attracting basin and figure out that it has to always be indiscrete. And we know also by their work that any point eventually lands in these big rings where you're a power map, which means that the relation is indiscrete. And this also, by the way, we have a concise proof using our theorem A and their work that this is the case. Okay, so I want to, in how much time I have left? 10 minutes. 10 minutes, good. So in the next 10 minutes, I want to give you an idea of the proof of theorem B, because I think it's cool. And I think I can say it because, well, because, well, how are we going to do it? So when we are looking at one-day domains, you can think of non-autonomous dynamics, let's say, or we many times think of maps from the disk to the disk. We could try to realize the dynamics we're looking for there, and then hopefully, this is what we do, use quasi-conformal surgery to plug these dynamics we've designed in an entire, as the orbit of an entire, of a one-day domain of an entire map. So this is the two steps that we have in our proof. So let's start with the first one. Let's try to design this. How would it look? How could I have these two components living in a same sequence of Blaschke products, so proper self-maps of the unit disk. And so for the step one, what we are going to do, and I think this idea is really cool and it's provided to us, so Curtis McMullen suggested we could try to mimic polynomial dynamics to construct this sequence. Let's see. So let's suppose we have a polynomial with an attracting basin. And let's surround this, the critical point on the Julia says of these polynomials by some curve. So for example, I have the rabbit. So we know that in the attracting basins, we have this grid relation. And now we know that the infinities and super attracting fixed points. So the orbit relation in the basin of infinity is in this grid. So I can say, if you let me, that these different relations coexist in this zero. But you can say, okay, what the wait, my points are going to escape this zero as I iterate. I know. So let's, but I will want to mimic my idea to generate this sequence of these Blaschke products will be to mimic the dynamics of P in the iterates of this zero in the Blaschke sequence. So how do we generate this sequence? Well, first of all, how do we choose this curve gamma 0? So let's just use Butcher coordinates, right? Let's take R large enough, and let's do the image under this Butcher's map. And well, that just generates gamma 0, and the 0 is the component surrounded by gamma 0. And well, I keep iterating my set to the D for the degree of the polynomial. And well, so I have these equipotential curves, they map to bigger one. I keep using the same map. So I have gamma 1 surrounding gamma 0, and I keep iterating this diagram commutes, and I have this gamma 2, gamma 3, gamma n. Okay, but these are larger and larger domains, right? And now to generate my sequence in the disks, well, I normalize, I just take some Riemann map that maps these D0, D1, the interior of the region enclosed by bounded region enclosed by gamma 1 and so on. And I just map them with other Riemann maps. Now this time, okay, above, I was always using the same map. Now we'll have to use different maps. But this gives me a sequence of maps in the unit disk. And observe that if we look at the rabbit, well, I'm contracting, right, to fit my picture in the disk. So in fact, these Blaschke products will be, they're hyperbolic, but they will be really contracting. Okay. Right. So I claim, but it requires some proof, but some work, but I claim that this process preserves the orbit relation that I had to the polynomial. Because, okay, if I take to get an idea about this, if I take a point here, well, the image will belong to gamma 1, to gamma 2, and I still have this sort of equipotential behavior curves. Okay. So I've generated this sequence of Blaschke products where orbit relations coexist. Now, this sequence of Blaschke products, this sequence, and also we have a more general definition, are uniformly, what we call uniformly hyperbolic. And what we mean by this is that, in this case, I've chosen this definition, in our case, that they fix 0, they're hyperbolic, And there exists a constant such that the distance, you can choose if you want the hyperbolic or the Euclidean distance between 0 and any critical point of any Blaschke product. So this is a uniform constant such that I always remain close to my fixed point here for all n. Okay, so this is our notion of uniformly hyperbolic. And of course, when I'm producing and generating my sequence of Blaschke products like this, well, definitely these are, and in fact, they're getting closer and closer. So they satisfy this definition. Okay, so that's step 1. And the step 2, this is nice, but what we wanted as a wandering domain, really. So now we want to try to plug in some entire map. So I need a definition of uniformly hyperbolic for orbits of wandering domains. So I'm going to say the function is uniformly hyperbolic in an orbit of simply connected wandering domains if, sorry, I should have said this as well here. These Blaschke products have uniformly bounded degree, okay? So here I'm saying now, my function restricted to these wandering domains has uniformly bounded degree. And there exists a constant such that I don't have a disk, right? I cannot uniform MIMEs to fix 0. So I'm just saying that the hyperbolic distance, if I follow one orbit in my wandering domain, then the hyperbolic distance between the critical points or that I might have in this UN remains uniformly bounded from the orbit of this point. And this definition doesn't depend on the point set that I might choose, the orbit I might choose to follow. Right, so suppose we can find a uniformly hyperbolic function with a uniformly hyperbolic sequence of wandering domains. What we want to do now is to replace the dynamics I had there in that uniformly hyperbolic wandering domain by those of the sequence Bn I've just generated. And to be more precise, as we did here when I had when I had here a Baker domain and I said we could take Riemann maps and look at these in periodic components by this diagram with the same Riemann map. Well, I can do the same with wandering domains. However, I'm not going back to the same picture. So when you have a 2-component in general, or now a wandering domain, I can just take Riemann maps from each of the wandering domain to the disk and define a map from the disk to the disk as going down, iterating the map in the disk, and up, or the other way around, right? I have 2 different Riemann maps like this. And these are called associated inner functions, because if I have infinite degree, they might not be Blaschke products, but for now, today they're Blaschke products. So what I want is that I have this Blaschke sequence, and I want to make it the associated sequence of inner functions for my new function f. Yes, this is the definition, what I just said. This sequence that I generate just by taking some Riemann maps is called a sequence of inner functions associated with my map restricted to the orbit. Okay, so this is our surgery theorem. So suppose we have a function that is uniformly hyperbolic in the wandering domains and a uniformly hyperbolic sequence of Blaschke products such that the degrees, and this is important, they agree at each step. Then there exists an entire function G such that G is conjugate to my original map outside these wandering domains under a quasi-conformal map phi. And now Pn is a sequence of inner functions associated with the new map, which is saying that now these are the dynamics in my, and these are the ground orbit relation, whichever the ground orbit relation was for the Blaschke sequence, well, this is preserved under topological conjugacy, so it will be for my wandering domain. And let me point out that this surgery result might be interesting on its own because we had to plug in it at infinitely many domains simultaneously. So we had to make sure our definition of uniformly hyperbolicity makes sure that we have these K quasi-conformal maps with some uniform K that allowed us to do this in all wandering domains at once, replacing the dynamics on them. So now with theorem C, theorem B follows with Bn as constructed, and F being the lift of a map with a superattracting basin of degree D. So, or if I chose a polynomial of degree 3, we could use my first example of these wandering domains that had a critical point map to a critical point map to a critical point of degree 3. As long as the degrees are the same, I don't care what happened in the wandering domain. Now I just replace it with my new Blaschke sequence. And my last slide. Just also, if you're interested in internal dynamics, in wandering domains, and which Blaschke sequences can be realized, well, a consequence of our surgery result or a corollary is that if you give me any uniform hyperbolic Blaschke sequence, I can find an entire function with an orbit of wandering domains for which this sequence is associated. And I think I'll stop here. Thanks for your attention.
Any questions? Oh, no, sorry. Łukasz.
I have one, if I still may. I haven't realized the limit of the question. So, so there's this beautiful division of wandering domains into 9 subtypes, which I'm sure you're familiar with.
Mm-hmm.
So do you know how this division goes into this grand orbit relations? So is there any results about how, which type is discrete and whatnot?
Well, in this case, the ones we construct are not just contracting, but they're also strongly contracting, yet another notion as sub notion there. And you've seen we can have discrete and indiscrete. So we think it's not just this plays a role, or if you have one-to-one, for example, some cases are easy. If you have a one-to-one, which they call eventually asymmetric, then it's going to be discrete. But otherwise, we think the geometry also plays a role, not just the contraction or non-contraction rate of what happens in the wandering domains according to that classification.
Nuria?
So just a comment that I think you stated that you could divide your wandering domain into 2 different components, but your picture in the rabbit already gives you infinitely many, right? Because the Julia set is precisely this S hat.
Yeah,
right?
we used another one for our proof, as said Landa said, but I like the picture of I like the picture of the rabbit, but you're right. I should have said this, yes. Although they belong to the same
grand orbit, right? So, but still, I mean, you could actually, by choosing your polynomial, you could break it into so many.
Yeah. So we stated for 2, but in fact, our construction holds for any polynomial. That doesn't
and any combination you want, and any because every polynomial can be plugged in, right? Thank you.
Yeah.
Any other question? Here,
So in this construction, what you get is near the boundary, you have indiscrete orbit, and inside you get discrete. That's always true?
Or whatever the polynomial had, right? If you had choose a polynomial with a single disk, you will get indiscrete.
But at least near the boundary.
Or if you sorry. If you have one with a single disk, because of this leaf thing, you will still get, sorry.
But the question is, near the boundary, you always get indiscrete.
Yeah, with this construction, yes, we do.
And another question is, instead of using this quadratic polynomial, just use a standard normal form for Blaschke product, and just choose where you put the zeros and so on, and can you control what you get?
Well, we are working this. We've been thinking about this for a while, and yes, we have some criteria. And in fact, we are working on this to generate examples where we are looking at the resulting dimension of the Teichmuller space associated with it. But as of today, we don't have yet the results we're looking for. Yeah.
Thank you.
Final remarks? That's it. So we continue in 5 minutes. Thank you again. So our last speaker for today is James Waterman from Stony Brook University. Yes, and he will speak about quasi-conformal equivalence of transcendental functions.
Thank you very much, Luca, and thank you to the organizers for organizing such a wonderful conference. So I today would like to speak about quasi-conformal equivalence of transcendental functions, and importantly, this is joint work with La Sorrempa. Okay, so I'd just like to get started with some of the basics. So I'm going to start with a fundamental result from complex dynamics that I'm sure everyone is very happy with, which is going to be Botcher's theorem. So for Botcher's theorem, what it says is that if I have two polynomials of the same degree, then they're going to be conformally conjugate in neighborhood of infinity. So this is for polynomials. In the neighborhood of infinity, and just to state it, so as I'm sure everyone's pretty happy with, we have two polynomials, say f and g, and they're of the same degree. Say d greater than or equal to 2. So then there exists neighborhoods u and v of infinity and a conformal isomorphism. So a one-to-one conformal map, formal isomorphism. Say phi from u to v with infinity fixed, so that f of phi of z is equal to phi of g of z for all z inside of this neighborhood that we have here u. So all right, so that's just stating some basics, but really, I think we'll all agree that this is one of the fundamental foundational results in complex dynamics, and many more powerful results and techniques come from this as a foundation. So for example, if you're talking about external rays, puzzle pieces, things like this, they all start from Botcher's theorem, and the fact that one has this conformal isomorphism in a neighborhood of infinity is going to be our starting point for today. So yes, for this talk, really though, instead of worrying about polynomials, what I like to consider are transcendental functions. So I'm going to start off with trying to talk about transcendental entire functions. So the obvious question from here that we'll start off with is, well, can we formulate, or could we attempt to formulate, a Botcher's theorem for transcendental entire functions? So is there some sort of analog of Botcher's theorem for transcendental entire functions? Let's say, well, for instance, f and g from C to C. So that's a first question that one could possibly ask is, can one attempt to formulate something somewhat similar in the setting for transcendental entire functions? And if so, well, here for Botcher's theorem, what one has is in particular the fact that these polynomials have the same degree is very important. So you have this conformal equivalence class near infinity, you can think is really just talking about whether or not the polynomials have the same degree. So in the transcendental setting, you could ask, well, if one was able to get such an analog, what would the analog of the degree be in this transcendental setting? So we could also ask, what is the analog of the degree in this case? Okay, so here's the questions as stated, but of course, it doesn't perhaps immediately seem clear why these questions even make sense at all. Because if you have a transcendental entire function, you have an essential singularity in infinity, so you don't have a nice invariant neighborhood infinity on which you could possibly wish to do have such a conjugacy here. So this already is saying that one has to be fairly careful. And really, what you have to do is not just look globally at points that are in some neighborhood infinity, but look at, say, points that under iteration stay near infinity. So we could try to look at an example or two and see for some example what might possibly happen. So one example is Fatou's function, which is z goes to z plus 1 plus e to the minus z. And so this function here, let's go up here. So this function here, more or less, what the dynamical plane for it looks like is that one has a right half plane, which is contained inside of a Baker domain. So if the real part of z is large, then this exponential term is small. And so really, this function here is just looking like translation. So one has a Baker domain over here. And similarly, if the real part is small, then the function is just looking like the exponential. And so in the left half plane, we'll have that the function looks like the exponential. So this is what one should think, at least near infinity, what is happening, that one has a Baker domain over here, and over here, the function looks like the exponential. And one might hope that if one had some analog of this result for all transcendental entire functions, then what you could think is, well, perhaps if not just having the same degree, but just I post-compose by some affine transformation. One would hope that still the dynamics and the behavior near infinity might somehow be similar. So let's look if instead of considering this function here, this z plus 1 plus e to the minus z, instead I consider the function z goes to z minus 1 plus e to the minus z. So now, instead of where here one translates to the right, now instead what one gets is you have infinitely many superattracting basins. So here one gets superattracting basins kind of in this region. Right here that replaces this Baker domain. So immediately one sees that just by post-composing with just subtracting 2 here, what one gets is that the behavior near infinity is markedly different. That over here one has a Baker domain, whereas here one has just these superattracting basins. And in fact, if one considered another example that we add a 2 pi I onto this, then we've taken our super attracting basins and turn them into escaping wandering domains. So where these super attracting basins just translate up by this factor of 2 pi I. So again, here, what we see is that the behavior near infinity for all 3 of these examples, even though on a function theoretic relation, they're very nicely related together, the dynamics near infinity is really completely different between these 3 examples. All right, so for general transcendental entire functions, this is really saying that the hope of a general Botch's theorem, there isn't so much. So what do we need to do? Well, we can shrink the class of transcendental entire functions that we want to look at. So instead, let's consider various classes of transcendental entire functions. And the classes that we will look at are the class S and the class B. So I'll tell you first off what the class S is. So Spicer class S is the class of all transcendental entire functions with a finite set of singular values. So this is the set of F from C to C that are transcendental entire functions for which the number of singular values here is finite. And here, by singular values, what I mean is that this is the closure of the asymptotic values and the critical values. So this is asymptotic values together with critical values, and we take the closure. So for example, the exponential function has no critical values, and it has an asymptotic value at 0. If you go along the negative real line, then you have that you're going to tend to the value 0. So you can think as well that these are finite singularities of the inverse function, if you'd like. Okay, so why? Well, what's one of the main reasons to study this class S? Well, in a sense, it shares many dynamical behaviors with polynomials. So in particular, one reason is that it has nice natural finite dimensional parameter spaces, which are given by quasi-conformal equivalence classes. So let me state a definition. So if F and G are transcendental entire functions, these 2 functions F and G are going to be called quasi-conformally equivalent. If there exists a quasi-conformal homeomorphism I guess I want 2 of them. So quasi-conformal homeomorphisms, phi and psi, which map from C to C. So that we have the following conjugacy. So phi of F of Z is G of phi of Z for all Z in C is what we have. So what you should think is that 2 functions F and G are quasi-conformally equivalent to each other if geometrically they map in the same way, is what this is saying here. Alternatively, you could have a diagram that nicely commutes. Both are reasonable ways to interpret this statement here. Okay, so these quasi-conformal equivalence classes are very nice. And in class S, we have that these quasi-conformal equivalence classes say if I have some function f that's transcendental entire function, and in the class S, then its quasi-conformal equivalence class, which maybe I denote M sub f, this forms a complex manifold of dimension the number of singular values of f plus 2, where this 2 comes from complex conjugation. All right, so I think besides giving an example of this continuing, that's basically for now what I want to say. If you want to know more about quasi-conformal equivalence classes, specifically related to class S and possibly beyond, you should see Gustavo's talk on Thursday. Okay, so just one brief example of this. Is let's just go back to our friendly old exponential function. So for our friendly old exponential function, it only has one singular value, this asymptotic value at 0. So you should expect, at least from my statement here, that the quasi-conformal equivalence classes, or the quasi-conformal equivalence class that the exponential function sits in, is of dimension 3. And in fact, if one is quasi-conformally or topologically equivalent to the exponential function, then it should be of the form lambda e to the az plus b, where lambda and a are non-zero, and b is a complex number. So this is the quasi-conformal equivalence class that the exponential function sits in. So while I stated this definition for transcendental entire functions, one could equally attempt to use it for polynomials. So I wanted to just give another motivating example, which are the two polynomials z maps to z cubed and z maps to z cubed minus z. Okay, so for these two polynomials that I have here, well, they have the exact same degree, clearly. So Butcher's theorem tells me that in a neighborhood of infinity, these two maps are going to be conformally conjugate to each other. Same degree, they're going to be conformally conjugate to each other. So, conformally conjugate in a neighborhood of infinity. But if one has a quasi-conformal, if these two were quasi-conformally equivalent, well, that should say that the critical points, counting, I guess, multiplicity, should be mapped as well to the critical points over here and preserved. So here one has just a single degree 3 critical point, and here one has 2 degree 2 critical points, and so clearly we're not going to be able to match these two up. So what one should get is that while we have a conformal conjugacy, we don't have that they're actually quasi-conformally equivalent everywhere. So this, I should say, is really near infinity, so in neighborhood infinity, but they're not quasi-conformally equivalent. Okay, so really, I guess all that example was meant to illustrate is that instead of looking at this slightly restrictive class of quasi-conformally equivalent maps, what is perhaps the more natural notion to do, is to look at those maps that are quasi-conformally equivalent, but relax not globally, but just somehow near infinity. So we're going to say two maps are eventually quasi-conformally equivalent, and we'll denote it, say F is quasi-conformally equivalent near infinity, or eventually quasi-conformally equivalent to some other map G. Both of these are transcendental entire functions. If there exist homeomorphisms, quasi-conformal homeomorphisms, formal homeomorphisms, phi and psi, again from C to C, so that we have the following: phi of f of z is equal to g of, g of phi of z, and that this occurs not everywhere, but just whenever either side is sufficiently large. All right, so perhaps a brief example of what I mean is one could look at the exponential function and ask, for instance, is the exponential function and the sine map, are they both eventually quasi-conformally equivalent to each other? And so in order to see this, well, that they aren't, is one can look at what happens to the preimage of the complement of a closed disk for both of these. So for the exponential, if one looks at the preimage of the complement of a closed disk, we get that this is going to be a right half plane, whereas for sine, if one does the same, then you get more or less a half plane here and a half plane here. And so in particular, you can think that near infinity, these two functions don't look alike. That here, one only has near infinity one component of the preimage, and here, near infinity, one has two components. So in order to be eventually quasi-conformally equivalent to the exponential, what you'd really need is that this preimage of your function, this preimage here, was a quasi-disk on the Riemann sphere. So in order to be in the same eventual quasi-conformal equivalence class to the exponential function. Correct. So it's whenever the maximum of this side or that side are sufficiently large. Yes. All right. So going back to the Speiser class S, or well, I guess we haven't really left yet. One would like to, well, just not leave the Speiser class, perhaps, but we have a problem, which is that the class S isn't invariant under these eventual quasi-conformal equivalence classes. So class S is not invariant under this equivalence. So what we would like is a class that is, and this is going to be the class B. All right, so what is the class B? So this is the Eremenko-Lyubich class B, and it is the set of transcendental entire functions from C to C, where for the Spicer class S, we had that the set of singular values was finite. Now all we want is that the set of singular values is bounded. So here, S of F is bounded or contained inside of some compact region is what we want for this class B. So I think now we have the background to state a version of, don't have it anymore, this Botch's theorem for transcendental entire functions. Okay, so this is due to Rempa from 2009. And more or less what this says is that if you have two transcendental entire functions in the class B that are eventually quasi-conformally equivalent, then with some extra hypothesis, this implies that one gets actually a quasi-conformal conjugacy. So we're going to suppose that we have F and G are transcendental entire functions in the class B. And moreover, they are eventually quasi-conformally equivalent to each other. So we have that F and G are eventually quasi-conformally equivalent to each other. Then there exists a quasi-conformal homeomorphism theta from the complex plane to the complex plane. It's a quasi-conformal homeomorphism. And what we want are this extra little bit. So we have two constants, r and say r tilde, which are both positive, so that we have this quasi-conformal conjugacy that theta of f of z is equal to g of theta of z. That we have this whenever either the iterates of f are always sufficiently large, always greater than this r, or the iterates on the right side are always sufficiently large. So when either the iterates over here are large, or mod g to the n of theta of z. Are large. Yes. Yeah. So yes, exactly. Yes. Not off the top of my head, no. So kind of the point of this talk is that trying to decide when two transcendental entire functions, or just transcendental functions in general, are or aren't quasi-conformally, eventually quasi-conformally equivalent to each other is not very easy, is, I think, more or less the idea. Okay, so this, I think, leads to, yeah. So easy. All right, so this leads to, well, exactly the following question, which is, suppose that I am given two transcendental entire functions, how do I tell whether or not they are actually eventually quasi-conformally equivalent or not? So how to tell whether two transcendental entire functions are or aren't eventually quasi-conformally equivalent. Okay, so and more or less the way that we're going to do this is a slightly more function theoretic breakdown of what these two functions actually, how they geometrically behave. So start off with what I'd like to say is, so suppose that we have some function, say f, that's in the class B. So it has a bounded set of singular values, is what this f has. So then if it's in the class B, what this says is that there exists some constant r, which is greater than 0, so that the singular values of f are all nicely contained in, say, a disk centered at 0 of radius r. So whether or not you want this to be a disk or just some Jordan domain doesn't really matter. Just for nicety's sake, we have, I'll specify this is a disk. So the picture that we have is the following. So yeah. So here, maybe it's better if I change. Yeah. Okay, so the picture that we have is that we have some disk, say, of radius r here, and the singular values are all contained inside of this disk. And our function f here is going to map over here, so one can look at preimages. So one could say, look at a preimage of this exterior component, and what we would get over here in the plane are some simply connected domains, which are called tracks. But for this, what I'm really interested in is the preimage of this disk that one has right here. So the preimage of this disk here, maybe different color is better. So the preimage of this disk here is going to be this simply connected region that one gets right here. And so what we have is, so first off, f is going to be a universal covering map on each of these simply connected components onto the exterior here. And we have a simply connected region here that's mapped onto this disk of radius r here. So because of the fact that this is a nice simply connected region, we can just uniformize it. So consider the Riemann map. Map this into the disk, and we could just normalize over here. So then what this says is that we get a map down here, say f bar, which maps the disk to the disk. So in particular, this map f bar, what we want to know is how it behaves on the boundary of this disk. So how it behaves here. And how it behaves on the boundary is going to be determined by looking at how it behaves on the boundary of these tracks that one has. So in particular, because of the fact that we have started up here with a transcendental entire function, this map f bar is going to extend analytically to an open dense subset of the unit circle. So it'll extend everywhere except for the singularities that one gets by going to infinity along here. Moreover, it's going to be a universal covering from the various, so you'll have some singularities here, which correspond to going in this direction. And inside of these components that one has here, it's going to be a universal covering onto the boundary of the disk over here. So F bar is also a universal covering of the boundary of the disk on each of these components that one has. Okay, so perhaps it would be good to have a slightly more simple, concrete example, which let's go with our favorite old exponential function. So here, we're going to have a right half plane is going to map onto the complement of a disk. So in particular, what this says is that a left half plane is going to map into the interior of this disk. And if one uniformizes on both sides, then what one gets is this disk here is going to map as a universal covering onto the punctured disk over here. So here is the exponential function, and here's the restriction of the exponential function from this left half plane. We've uniformized to the disk, and then we've mapped over, is what we have. So for all of this, really, and for the setup that we have, what we're interested in are the boundary values of this map F bar here. And really the whole point of this is that the boundary values of this map F bar are going to tell us a lot of information about what the quasi-conformal equivalence classes of this map F have to be. So yes. Sure. So one can uniformize to have a singularity, say, at 1. And then, so I'll get back to this picture and that picture in a second when I try to talk a little bit more. But yes, thank you. So yeah, we'll have a singularity, say at 1, from the fact that if you will go in this direction, then you'll have some singularity of your Riemann map. Okay, so all of this, really, what we want is this whole setup is in order to try and simplify and decide when two maps are or aren't eventually quasi-conformally equivalent. And so the answer is if we let F and G be in class B, and we do the exact same procedure to both F and G, and we obtain these restrictive functions, then we can decide whether or not they are eventually quasi-conformally equivalent based on their quasi-symmetry class of what's occurring on the boundary of the disk. So, those guys as say above, then F and G are eventually quasi-conformally equivalent is the same as there exists a quasi-symmetric map, say phi, on the unit circle, so that F bar is G bar composed with phi on S1 as well. It's except for the singularities that one has. So where this is defined. Okay, so in a sense, what one's done is taken this two-dimensional problem of trying to determine what the two-dimensional quasi-conformal equivalence class of these two maps is, and reduced it to a one-dimensional problem of just trying to find quasi-symmetric maps for which one has this relation. So in particular, really, if you want to think about it as the geometry of what the actual function is doing, the behavior on the boundary of these level curves is exactly what's determining the quasi-conformal equivalence classes, the eventual quasi-conformal equivalence classes. Okay, so one can say, in fact, a little bit more than just that one has this quasi-symmetry on the whole boundary, and really all that's important is exactly what's happening with the preimage of a single point. So, yeah. Yes. Yes, it should. Yes. So it just correspond to the various accesses to infinity. Okay, so as a corollary, we have, let's say, f and g in class B, and again, f bar and g bar as above. So then f is going to be eventually quasi-conformally equivalent to g, is the same as I just have the f, the preimage of, say, 1, and the preimage of for f under 1 and the preimage for g under 1. Guess I want that agrees up to quasi-symmetry. So if one, say, looks here for f, we could take this point here at 1 and look at its preimages. And so what'll happen is you'll have a bunch of preimages here that are going to accumulate at the singularities of my function on the disk. And the geometry of how they accumulate and the comparison of the size of these intervals here for f bar compared to g bar is exactly what tells you what the quasi-conformal equivalence classes are going to be. Sorry? Correct. You could take, so on this side, there shouldn't be any singular. So one's just a nice choice. So yes. Okay, so in fact, I had this example for, we had the exponential function sine. So the reason why they weren't eventually quasi-conformal equivalent was you do the same thing, but for the sine, you have 2 tracks versus the exponential, you have 1. So near infinity, they just won't map in the same way. But you could ask, well, what if I have 2 functions that have the same number of tracks? So like, for instance, e to the z squared and sine, both with 2. How would you determine which of the 2, whether they are or aren't eventually quasi-conformally equivalent? And you could just compare exactly what is happening to preimages on the unit circle. Or if you wanted to stick with this picture here, well, for one of them, for the sine, what you get is that the complement is just going to be a strip, whereas for the other, in this picture, one would have the complement contains a sector. And so when you map to the disk, the comparison of the intervals of this partition are going to be very different, is the picture that one has. So just to, yeah, okay. So just to finish up, all of this with defining this function f bar, I started with a transcendental entire function. But there's really no need to start and have it come from a transcendental entire function. You could start just with a map from the disk to the disk, for which you have this property that this map extends analytically to an open dense subset of the circle, and it's a universal covering on the boundary. So you don't worry whatsoever as to whether or not it comes from an actual entire function. You just consider a map on this region, and just this map f bar, and all of these things still go through. So determining the eventual quasi-conformal equivalence classes of those maps is exactly the same. That one can consider the same thing. And this is, in a sense, I guess, somewhat important because recently there's been a fair bit of interest in transcendental functions that aren't entire. So transcendental functions that are perhaps just defined on some open dense subset of the plane, or some simply connected Riemann surface, or something like this. I think that's a reasonable place to stop. Thank you.
Thank you for the talk. Any questions? Yes.
Yeah, thank you for your talk. I was wondering how this question goes in the setting of like just finite type maps.
Yeah, so finite type maps would encompass basically everything here. It's just that in this set, so exactly. So if you had a finite type map, then it would have this property of you have some region that's defined, you map it into the disk. But in this setting, you can say more about, I guess, the quasi-formal equivalence classes.
So I was more like curious about, like for finite type maps, we have this combinatorial construction of line complexes.
Yes. So one might hope that you get a similar thing in this picture. But
do you think that there might be some just like combinatorial conditions? So you just, I don't know, suppose you have two maps of finite type is, say, well, the same set of singular values. And then you like draw a line complex, and then you kind of look just on combinatorics.
So yes, it seems very plausible that you have exactly the same thing. Yes.
Okay. Oh, great. Thank you.
Right. So thanks for the talk, James, and thanks for the free advertisement. Is there any way, or like, do you know of any conditions under which you can extend eventual QC equivalence to QC equivalence on the whole plane?
So not off the top of my head. In general, eventual QC equivalence is a far broader class of maps. So I'd say no, not off the top of my head. Not a good one.
Thanks, James.
Yeah.
We have another question.
Yeah, thanks for this talk. I just want to ask, could you comment a bit on how you exactly get this quasi-symmetric map? And especially, do you get any explicit bounds on this quasi-symmetric constant? How exactly?
So in a sense, the quasi-symmetric constant would come from, you'd look at two different, I guess, transcendental entire functions, or two functions, an f bar and a g bar, and you then get, from pulling back this arbitrary point that you've picked, some partition of the unit circle, and you compare what these intervals, the sizes of the adjacent intervals. I guess you could do this by some extreme length argument or something like this, but nothing that concrete so far.
But could you get some explicit expression for it in terms of maybe like depending on the geometry of tracts or something?
This seems very likely, yes. Yeah, so for example, if one of your tracks, the complement was a strip and the other contained some other nice set, then one could probably get some nice bounds. Yes.
Thank you.
Oh, yeah.
So could just how does this relate to the order of growth? So
So for you can have two functions in the class B, which are eventually quasi-conformally equivalent and have different orders of growth. So I think in general that there's not a huge overlap. So
do you have an example of that?
there probably is one. I would have to stop and think. Yeah.
Another question there, Gustavo?
Some examples by Fisher on functions that are equivalent but have different orders of growth, but there's some bounds on what the orders should be if they're both like forms of infinite.
I have one more question. So this is not a conjugacy, but it's just equivalence.
Yes.
For example, can you say something about whether like these two maps F and G, if they are quasi-conformally equivalent, do they share any dynamical properties as well, or this completely
so
off the grid?
Yeah, it should be that if they are actually quasi-conformally equivalent, then the functions themselves geometrically are going to look the same. So one should have a nice description between the two. Yes.
Okay. Any other questions? So let's thank the speaker again.